Welcome back to Sleepless Mysteries. When astronomers first spotted 3I Atlas on July 1st, 2025, it appeared to be a lone traveler, a glowing comet drifting into our solar system from the deep between stars. But as telescopes tracked it closer, something strange emerged. It was not alone. Surrounding Atlas is a swarm of smaller, darker objects, fragments, clusters, or perhaps something stranger, that move as if bound to it, yet refuse to behave like ordinary debris. A visitor from another star is already unsettling. A visitor carrying a swarm is something else entirely. At first glance, scientists thought they were simply fragments shed from the comet itself, pieces of ice and rock breaking away under the sun's heat. But the behavior of this swarm defies expectations. Instead of scattering into empty space, the fragments seem to cluster, orbiting around Atlas like a cloud. Some move in formation, some drift outward only to spiral back again, and their darkness makes them nearly invisible, detected not by light, but by the faint ways they block the stars behind them. It is as if Atlas carries a hidden entourage through our skies. The implications are profound. If these are natural fragments, then Atlas is larger and more unstable than we believed, shedding parts of itself as it crosses into the warmth of our system. But if they are not natural, if their clustering suggests structure or design, then we may be staring at a phenomenon no science yet explains. A cometary body with companions, a mothership with drones, a mystery written in darkness, drifting silently past the worlds we know. This isn't the first time strange behavior has been linked to interstellar visitors. In 2017, Oumuamua accelerated in ways no comet tail could explain. Some suggested it was a probe pushed by sunlight on a thin, sail-like surface. Borisov in 2019 carried chemistry that puzzled researchers. Now Atlas arrives with a swarm, an escalation in the pattern of the unknown. 3 visitors, 3 anomalies. Are they coincidence or part of something larger? Ancient traditions may echo these fears. Texts from Mesopotamia speak of companions of the torch star, smaller lights following a great fire in the sky. The Maya described gods traveling with attendants of light. Even medieval chronicles describe comets splitting into multiple bodies, a celestial host spreading across the heavens. Were they witnessing natural fragmentations or something more deliberate, a truth we are only now rediscovering with telescopes and instruments? You don't need the telescope images to imagine it. Just let these words guide you. Close your eyes if you wish. Picture the black void of space, scattered with stars. A glowing comet drifts forward, green light spilling from its surface. But around it, darker shapes move in silence, revealed only when they blot out the stars. They swarm, they cluster, they follow. The comet is not alone, and neither are we as we watch. Before we begin, if you haven't already, subscribe to Sleepless Mysteries so these quiet journeys into the unknown will always find you. Tap the like button if this story sparks wonder. And if you're still awake, share in the comments where in the world you're listening from and what time it is right now. Now, let the noise fade. The comet moves, the swarm follows, and the questions deepen. What are the dark objects surrounding 3I Atlas? And what do they mean for us, the swarm of shadows? When astronomers first noticed 3I Atlas cutting across the night sky, their instruments told them this was no ordinary comet. Its path was interstellar, meaning it hadn't been born in our solar system. That alone was enough to cause excitement, but soon a stranger detail emerged. Around the glowing nucleus of this icy visitor, darker forms seemed to drift, lingering too close and too organized to be random debris. Some scientists quickly dismissed these spots as distortions, glitches in imaging, or clumps of dust. Yet the more telescopes tracked it, the more persistent the pattern became. A swarm of dark companions circling the alien traveler. The idea of a swarm unsettled people because it raised 2 possibilities, both unsettling in their own way. The first was natural but still dramatic. Fragments breaking away from the main body, pieces of ice and rock scattering, but somehow maintaining proximity as though bound together by invisible forces. The second was the one that captivated imaginations. What if these weren't mere fragments, but entities, artificial or otherwise, accompanying 3I Atlas through its long voyage? Even respected astronomers who scorned speculation admitted that the swarm, if real, demanded explanation. It was unlike anything they had observed in the behavior of ordinary comets. Skeptics argue that swarms form whenever comets near the sun. Outgassing, violent bursts of sublimating ice, and gravitational influences could easily eject fragments that cluster nearby. In theory, this should scatter over time, but in the case of 3I Atlas, the supposed swarm appeared unusually stable. Its fragments did not trail in a long tail the way cometary debris typically does. They seemed instead to hover close, almost escorting the comet like a guard of silent sentinels. If this was only dust, it was dust with oddly disciplined behavior. One team using polarized light studies noted that the surrounding cloud of particles had peculiar reflective qualities. Rather than scattering sunlight the way most icy dust would, these objects absorbed more than expected. Their darkness was striking, almost as though they were made of carbon-rich material, something closer to asteroid fragments than comet fluff. If so, the question deepened. How could such heavy, solid clumps linger so close instead of falling away? The swarm was beginning to look less like a random spray and more like something with structure. This appearance was enough to stir echoes of past mysteries. When Oumuamua streaked through the solar system in 2017, it too confounded scientists with its odd shape and acceleration. Avi Loeb and others had dared to suggest it might be artificial. Now with 3I Atlas, whispers resurfaced. Could a swarm be evidence of engineered fragments, probes, or devices traveling together? If civilizations elsewhere launch craft into interstellar space, wouldn't they appear strange, alien, and difficult to interpret just like this? Most scientists urged caution. There were still no confirmed observations of artificial behavior, only oddities. But history has shown how fast speculation spreads when humanity encounters the unknown. Adding to the intrigue, observers noticed a sunward plume, a stream of material pointing directly toward the sun instead of away from it. This ran against the physics of solar wind, which should push material outward. Was this plume related to the swarm? Could the dark companions have shaped or influenced how the comet's gases were venting? Or was the entire system simply undergoing chaotic, poorly understood physics in its icy core? The deeper researchers dug, the stranger it appeared. At the heart of the puzzle is 3I Atlas's composition. Spectroscopic data revealed a coma dominated by carbon dioxide with water in unusually small amounts. This is unlike the typical comets studied within our solar system. In fact, the CO2 to H2O ratio measured by the James Webb Space Telescope was among the highest ever seen. If the dark objects were chunks of this same unusual chemistry, it could explain their strange appearance. But if their makeup differed from the core, it might point toward a more exotic story. Perhaps the comet had captured alien fragments during its interstellar journey, carrying them like stowaways across light years. And the size of the main body itself complicates matters. Estimates put its nucleus between a few hundred meters and almost 3 kilometers wide. If it leans toward the larger end, then the gravitational pull could conceivably help keep fragments close for a while. But even then, it should not produce a neat escort formation. Gravity from such a small object is feeble, easily overcome by solar tides. Yet the swarm lingered, drawing suspicion. If the estimates lean toward the smaller size, the anomaly only sharpens, because then its ability to hold companions fades almost entirely. One recent study used polarimetry to probe the dust and revealed deep negative polarization, another odd marker rarely seen. This suggests that the grains might have a layered or crystalline structure, bending light in unusual ways. If so, the swarm may not be made of solid rocks, but of exotic dust behaving unlike anything encountered before. Such results leave the door wide open. Was this a clue pointing to natural but rare interstellar chemistry? Or did it hint at something we simply lack the categories to explain? Meanwhile, conspiracy theorists latched onto the imagery, insisting that the swarm resembled craft in formation. Online communities spread claims that 3 Atlas was not a comet at all, but a mothership dragging along its smaller craft. Scientists groaned at such leaps, but they couldn't erase the allure of the narrative. Humanity is primed to see patterns, and when shadows gather around an alien visitor, the story writes itself in the imagination. Natural explanations remain the strongest candidates. Fragmentation happens. We've seen it with comet Shoemaker-Levy 9, breaking into pieces before crashing into Jupiter, or with countless comets that shed material under solar stress. But in most of those cases, the fragments fly off visibly, stretched into lines by gravity and momentum. In this case, the supposed dark companions hang close. Observers are waiting eagerly as 3I Atlas nears its closest approach to the Sun, to see if the swarm disperses or holds its form. If it scatters, the mystery may fade. If it tightens, the questions will only deepen. For now, the swarm of shadows remains an unresolved spectacle. A cluster of shapes, maybe no more than clumps of dust, maybe something entirely different. Each telescope pass adds data, yet the core mystery persists. Why does an interstellar visitor carry an entourage of darkness across the void? Until clearer answers arrive, all we can do is watch as this swarm follows its master through the cosmic night, a procession whose meaning remains hidden. What is 3I Atlas? When the faint signature of a moving object first appeared on the Wide Field Survey cameras of the Asteroid Terrestrial Impact Last Alert System, better known as ATLAS, in July of 2025, astronomers knew they had stumbled onto something remarkable. This was not the ordinary track of a near-Earth asteroid or a long-period comet. The path cut across the solar system with too much speed, too sharp an angle, and none of the telltale signs of belonging to the Sun's gravitational family. Almost immediately, orbital calculations revealed the shocking truth. This icy wanderer had come from far beyond our own star. Its official designation became 3I Atlas, marking it as only the third known interstellar object ever detected. To grasp the importance of that simple code, it helps to unpack it. The I in its name stands for interstellar, a category astronomers had only added to their catalog in 2017 with the discovery of the elongated mystery Oumuamua. The 3 marks its place in that tiny list of known visitors. Before Atlas found it, there had been only 2. Oumuamua, with its cigar-shaped body and unexplained acceleration, and Comet 2I Borisov, which looked more like a traditional comet with its bright coma and tail. With 3I Atlas, humanity now had a third example. And from the very beginning, it defied expectations by showing behavior that didn't neatly fit into either category. The first thing to note was its trajectory. Calculations showed it traveling on a hyperbolic orbit, meaning it wasn't bound to the Sun. Its eccentricity, essentially how stretched out the orbit is, was greater than 1, proof it came from interstellar space and would leave again after swinging around the Sun. That alone makes it a cosmic rarity. Every time one of these objects enters the solar system, it's a once-in-a-lifetime chance to study material forged around other stars. Unlike comets born in our Oort cloud, 3I Atlas carried chemistry, structure, and history that were alien to our neighborhood. But the surprises piled up quickly. Observations from the James Webb Space Telescope revealed something no one expected: the coma. The glowing cloud of gas and dust surrounding the nucleus was dominated not by water vapor, as is typical for comets near the Sun, but by carbon dioxide. In fact, the CO2 to H2O ratio was one of the highest ever measured in any comet. This was like finding a recipe from a foreign kitchen. Evidence that whatever star system 3I Atlas originated in, its ingredients were mixed differently than ours. Some speculated this hinted at a colder birth environment, as perhaps a far-flung icy region around another star where water was locked solid, but carbon dioxide could still sublimate. Another oddity soon caught the eye of astronomers: a plume of dust streaming sunward. Normally, solar radiation and the solar wind push a comet's tail away from the Sun. Yet here was a plume stretching toward it, a phenomenon that defied standard comet physics. Was this a case of asymmetric outgassing from the nucleus, jets blasting material in unusual directions, or was it a deeper mystery, hinting at forces scientists had yet to fully grasp? The images provoked debate, and in that debate, the mystique of 3I Atlas grew. The size of the nucleus was another puzzle. Early Hubble data suggested it could be as small as a few hundred meters across, or as large as nearly 3 kilometers. That range left a lot of uncertainty. If it was on the smaller end, then its observed brightness required unusually reflective materials, perhaps icy crystals shining in sunlight. If it leaned toward the larger end, then the mass estimates became staggering. Tens of billions of tons, enough to classify it as an interstellar mountain of ice and rock. One group of researchers even claimed it might be anomalously massive for its size, raising eyebrows and fueling speculation about what it might really be. From there, the mystery deepened into the microscopic. Polarimetric observations, the study of how light scatters off dust, showed that the particles in its coma behaved strangely. They reflected and polarized light differently than most solar system comets. In some wavelengths, they absorbed more than expected, suggesting a composition rich in dark, carbon-heavy grains. In others, they showed unusual crystalline scattering. These clues hinted at material forged under different stellar conditions, dust that had journeyed between stars before entering our skies. As data accumulated, scientists began tracing possible origins. By running orbital models backward through time, astronomers concluded that 3I Atlas likely came from a distant star system and had wandered for millions, perhaps billions, of years before intersecting with ours. Some models even suggested that interstellar comets like Atlas might outnumber stars in the galaxy. If so, then space between the stars is littered with icy nomads, fragments thrown out of forming planetary systems. Each time one strays into our sun's influence, we are granted a fleeting glimpse at the diversity of worlds beyond our own. And yet, no scientific discussion about interstellar visitors would be complete without mention of the more radical ideas. Some researchers, recalling the heated debates around Oumuamua, wondered aloud if 3I Atlas might be something more than natural. The odd plume, the dark companions rumored to surround it, the unusual chemistry, all of it made fertile ground for speculation. Avi Loeb, who had already proposed that Oumuamua might be artificial, once again stirred controversy by suggesting that we should at least consider the possibility of technological origin. Could 3I Atlas be a probe, a piece of interstellar engineering? Mainstream astronomers rejected this interpretation, preferring natural explanations. Still, the idea clung to the public imagination, because nothing excites like the hint of contact with the unknown. For all the speculation, what remains undeniable is that 3I Atlas is an unprecedented scientific opportunity. Unlike Oumuamua, which was faint and fast, this object is brighter and more accessible to study. Unlike Borisov, which resembled a familiar comet, Atlas brings chemistry and behavior that stand apart. It sits somewhere between the two, bridging categories and challenging assumptions. Its CO2 dominance suggests interstellar diversity. Its plume hints at unexplored physics of comet activity. Its possible swarm raises questions about fragmentation, stability, or even companionship. To the casual observer, it may just look like a speck of light in the sky, but to astronomers, it's a cosmic messenger. Every spectrum taken, every light curve analyzed, every faint shadow measured adds to a library of knowledge about the broader galaxy. For centuries, humans wondered what materials, what dust, what icy rubble circled other stars. Now, one of those fragments has come directly to us, trailing its secrets across the night sky. And so, when we ask, what is 3I Atlas? The answer resists simplicity. It is an interstellar comet, yes, but also a scientific enigma, a window into alien chemistry, a catalyst for wild speculation, and a reminder that the solar system is not isolated. It is a crossroads where visitors can arrive unannounced, carrying stories written in ice and dust. Whatever final truths astronomers uncover about its size, mass, and composition, one fact will remain unshaken. 3I Atlas is proof that the universe still surprises us, that the unknown still wanders into view, and that mysteries as vast as the galaxy itself can sometimes appear as nothing more than a smudge of light on a survey camera. Why swarm talk? When 3I Atlas was first spotted, astronomers expected the usual signs of an interstellar comet: a faint nucleus, perhaps a halo of gas, maybe even a tail. But soon after its discovery, chatter began to emerge from amateur observers, online astronomy forums, and even professional circles. Images taken of the object seemed to show more than just a single glowing body. There were shadows, specks, and dark companions drifting suspiciously close. The whispers began almost immediately. Was there a swarm of objects traveling with this interstellar visitor? The word swarm carries heavy weight. In astronomy, debris is common, but debris scatters. It trails off into faint lines, smeared out by motion and sunlight. What made 3I Atlas different was that some of the objects seen around it didn't appear to trail. They hovered nearby, clustered almost like a loose escort. Observers described it as though the comet was carrying an entourage of dark satellites across the solar void. To skeptics, it was nothing more than imaging noise or dust grains lit in unusual ways. To others, it was the start of one of the strangest astronomical puzzles of the decade. Part of the fascination lies in comparison. When comet Shoemaker-Levy 9 broke apart in the 1990s, its fragments stretched into a clear line, a cosmic string of pearls, before colliding with Jupiter. When Borisov entered our solar system in 2019, it fragmented as well, its smaller pieces quickly scattering and fading. In both cases, the behavior matched expectations. But if the dark companions around 3I Atlas were real fragments, they were stubbornly refusing to follow those rules. They seemed too close, too stable, and in some images too dark to fit the profile of ordinary comet dust. Theories spread quickly. Some argued the swarm was evidence of fragmentation, chunks breaking off the nucleus but held nearby by faint gravitational attraction. But that explanation had a flaw. 3I Atlas, even if it were several kilometers across, simply doesn't have the gravitational pull to hold companions for long. The sun's gravity would overwhelm it, scattering fragments downrange. Others suggested electrostatic effects, charged particles interacting with solar wind and magnetic fields in ways that allowed clumps of dust to cling together like invisible magnets. While plausible, this too was unproven, and it did little to explain the organized appearance that some swore they saw. What gave the swarm theory more fuel were the strange reflective properties of the supposed companions. Polarimetric measurements suggested that the dust surrounding 3I Atlas absorbed light differently than ordinary comet material. Instead of scattering sunlight in familiar ways, the swarm appeared unusually dark, almost invisible in many wavelengths. That odd darkness is what gave rise to the phrase, swarm of shadows. Unlike the bright coma of Borisov or the glittering dust tails of solar system comets, these companions seemed cloaked as if made of something more akin to asteroid rock or carbon-rich rubble. Some scientists attempted to calm the frenzy. They explained that when astronomers push their instruments to the limit, faint smudges and patterns can look like companions when they are simply noise. Image stacking, long exposures, and background star contamination can all create illusions of dark shapes. But the persistence of the reports made the idea hard to dismiss outright. Amateurs and professionals alike kept pointing to the same features, insisting that there was something there. Even if it turned out to be nothing more than clumps of ejected debris, the question remained, why was this object shedding material in such a way that it mimicked structure? Speculation outside the scientific community took a far more dramatic turn. The idea of a swarm naturally led to comparisons with science fiction. Fleets of alien probes, smaller craft traveling with a mothership, or self-replicating fragments deliberately designed to spread. On social media, images of 3I Atlas were circulated with captions suggesting it was a vessel, not a comet. Some tied it to old prophecies, others to Avi Loeb's controversial suggestion that interstellar visitors might sometimes be artificial. Once the phrase "swarm of dark objects" took hold, it was nearly impossible to pull it back into the safe harbor of cautious science. But even within scientific circles, the oddities wouldn't let go. The sunward plume observed on 3I Atlas, material inexplicably streaming toward the sun, was cited as a possible clue. Could this plume be connected to the swarm? If the nucleus was venting gas in unusual directions, it might fling fragments in unexpected ways, keeping them close rather than ejecting them far into space. But that theory too had limits. Gas jets are chaotic, unpredictable. To maintain companions that lingered in apparent formation would require remarkable coincidence or an unknown physical mechanism. The mass estimates added another layer to the puzzle. Some reports suggested that 3I Atlas was far heavier than its size alone would predict, hinting at a dense or exotic composition. If true, its gravitational field might exert slightly more influence than expected, enough to shepherd fragments. But even then, shepherding a swarm is no simple feat. Gravity from a comet is minuscule compared to the pull of the sun. Only something unusual, either about the material of the fragments or the way they were ejected, could make them stay in place. And then came the more exotic proposals. What if the swarm wasn't material from 3 Atlas at all? Some theorized it could be captured interstellar debris, objects it collected during its long journey between stars. Imagine the comet as a hitchhiker dragging behind it a trail of rubble gathered over eons, a cosmic vacuum sweeping up relics from alien systems. This idea fired the imagination. Perhaps those fragments were pieces of other worlds, evidence of chemistry or geology far beyond Earth's reach. If true, then the swarm wasn't just about one comet, it was a museum of galactic history following a frozen core through the void. Skeptics, of course, point out that extraordinary claims require extraordinary evidence. Until clearer imaging confirms the companions, the swarm may remain little more than rumor amplified by the human tendency to see patterns where none exist. Astronomers caution that we have only a small window to study 3 Atlas before it fades back into the interstellar dark. If the swarm is real, it will take every available telescope, from Hubble to JWST to ground-based observatories, to prove it. And even then, proving the nature of those companions will be even harder. Are they solid? Are they transient? Or are they illusions born of scattered light and hopeful imagination? Still, the allure persists. The phrase "swarm of dark objects" resonates because it captures something primal, the fear and fascination of the unknown. If space holds fleets, fragments, or shadows traveling together, then the cosmos is not the empty void we imagine. It is alive with mysteries that can slip into our solar system unannounced. Whether the swarm is no more than peculiar comet dust or something far stranger, it has already done what few astronomical discoveries manage. It has made the public look up, wonder, and ask questions that blend science with the oldest myths of watchers in the sky. And so the talk continues. Each new observation brings both data and debate, feeding the story rather than ending it. Some await confirmation of ordinary fragmentation, others cling to the hope of something extraordinary. But everyone agrees on one point. 3 Atlas has brought with it not just icy chemistry from another star system, but a cloud of questions as dark and elusive as the swarm itself. Until the mystery resolves, the phrase will linger like the shadows it describes, haunting, provocative, and impossible to ignore. Cometary activity and coma, dust behavior. To understand the mystery of 3I Atlas, it helps to return to first principles. What happens when a comet becomes active? In the solar system, most comets originate in the distant Oort cloud, or Kuiper belt, frigid reservoirs where ice and dust lie dormant for billions of years. When such a body drifts inward and sunlight begins to heat its surface, its frozen volatiles, water, carbon dioxide, carbon monoxide, sublimate directly from ice into gas. This process ejects material outward, creating a glowing coma around the nucleus and a tail stretching away from the sun. For centuries, this behavior has defined comets. Yet with 3I Atlas, the expected rules only partly apply. At first glance, the cometary activity of 3I Atlas looked familiar. Telescopes detected a diffuse halo of material surrounding the solid nucleus, a classic coma that brightened as it neared the inner solar system. But when astronomers analyzed the spectrum of this coma, they found something astonishing. Instead of being dominated by water vapor, as is common with comets from our own system, the gas cloud was rich in carbon dioxide. Observations from the James Webb Space Telescope confirmed that the CO2 to H2O ratio was unusually high, among the most extreme ever measured. This single fact upended assumptions. It suggested that 3I Atlas had formed under conditions unlike those of the comets we know, perhaps in a region of another star's disk where water ice was locked down, but carbon dioxide could still evaporate. The coma's chemistry was only the beginning. As astronomers traced its structure, they noticed asymmetry. Instead of a neat, round halo expanding evenly outward, 3I Atlas displayed plumes and jets firing from specific regions. This kind of jetting is not unheard of. Comets often vent gas through localized cracks, but one plume in particular stood out. It streamed sunward, directly toward the very star that should have been pushing all material away. This so-called sunward plume made no immediate sense. By all laws of physics, the solar wind and radiation pressure should have blown such material outward. Why would dust and gas defy the sun's push? Some scientists suggested that the plume was the result of unusual surface geometry. Perhaps a deep vent on the nucleus blasted gas so forcefully that it overcame solar pressure, momentarily sending material inward. Others argued it might be a trick of perspective, the tail angled in such a way that it appeared sunward when in fact it was slightly off. But as more observations accumulated, the anomaly held. The plume seemed real. If so, it represented a kind of cometary activity never cleanly documented before, adding to the growing list of 3 Atlas oddities. Then came the dust. In ordinary comets, sublimation carries dust grains off the surface, creating the coma and tail. These grains scatter sunlight, making the comet bright and sometimes colorful. With 3I Atlas, however, the dust behaved strangely. Polarimetric studies, those that measure how light is polarized after bouncing off particles, showed that the coma had an unusually deep negative polarization branch. In simpler terms, the dust was absorbing and scattering light in ways that did not match the common profiles of solar system comets. The grains seemed darker, possibly richer in carbon, or structured in exotic crystalline forms. This explained why some images showed the surroundings as unusually shadowy, leading to the famous phrase, "swarm of dark objects." The behavior of this dust cloud fed directly into the speculation about companions. If the coma contained large, dark clumps rather than evenly distributed fine grains, it might easily appear as though distinct bodies were trailing the comet. Indeed, high-resolution images sometimes showed blobs within the halo, as though the comet was surrounded by satellites. Scientists cautioned that this could be no more than clumps of dust, but the behavior of these clumps was still unusual. Instead of dispersing into a diffuse tail, many of them appeared to remain close, giving the impression of stability. The question then became, what physical processes could explain such stubborn dust behavior? One possibility involved electrostatic cohesion. Tiny dust grains in space often become charged by solar radiation, and charged particles can sometimes cling together, forming larger clumps. If this happened near 3I Atlas, the result might be stable, dark clusters orbiting or lingering around the nucleus. Another idea pointed to outgassing cycles. If jets were firing intermittently, they could create pulses of dust that temporarily held together before spreading out. Such bursts might produce the illusion of a swarm when seen through telescopes. Even more intriguing were the implications for interstellar chemistry. The fact that carbon dioxide dominated over water suggested that 3 Atlas originated in a colder, perhaps more distant zone of another star system. In those regions, water would remain locked as solid ice, while CO2 could sublimate more easily. If true, then the dust grains around the comet might contain exotic ices, organics, or even crystalline materials unlike anything found in our comets. Already, some researchers speculated that the unusual light scattering could hint at layered structures, possibly thin coatings of carbon or silicate mixed with volatile ices. If 3I Atlas was built from such exotic materials, then its coma was essentially shedding pieces of an alien world into our skies. The activity of 3I Atlas also raised questions about survival. Comets from interstellar space spend millions of years wandering in the cold between stars. When they finally approach a sun, their pristine ices erupt violently. For 3 Atlas, the violent jets and possible fragmentation hinted that the object was under tremendous stress. Some astronomers wondered whether it might disintegrate entirely before completing its passage. Others suggested that its apparent sturdiness, still bright, still coherent, meant it had a stronger structure than anticipated. Each possibility mattered because disintegration could scatter more fragments into the supposed swarm, while survival would allow longer-term observation of its unique chemistry. A parallel was drawn to Comet Borisov, the second interstellar visitor, which displayed strong activity but resembled solar system comets in its overall behavior. By contrast, 3I Atlas seemed to be rewriting the rulebook. Its CO2 dominance, sunward plume, its dark dust, all combined to mark it as something other than ordinary. Where Borisov showed kinship with comets we already knew, Atlas revealed difference. In that difference lay the potential to broaden our understanding of how planets and stars form elsewhere in the galaxy. Even more tantalizing was the link to panspermia theories. If comets like 3I Atlas carry organics or exotic carbon-rich compounds, and if their dust grains remain stable in swarms or clumps, then they could serve as delivery mechanisms. Dust from interstellar comets could seed planetary atmospheres with complex molecules. If Earth itself was once bombarded by such visitors, then life's ingredients might trace back to these alien wanderers. The coma and dust of Atlas thus weren't just pretty astronomical phenomena. They could represent a key step in the cosmic chain of biology. For the public, though, the coma and dust behavior had a different allure. The images of the strange plume, the dark shadows around the comet, and the mysterious companions sparked imagination. Was this really a natural process, or was something more deliberate at play? Even if most astronomers cautioned restraint, they couldn't fully dismiss the mystery. The data did not fit neatly, and until it did, the questions would remain. In the end, the cometary activity of 3I Atlas reminds us how little we know about the universe's diversity. Comets are simple in concept, ice and dust heated by sunlight, but in practice, each one tells a different story. With this visitor from another star, the story is stranger than most. Its coma glows with unfamiliar chemistry. Its plumes defy direction. Its dust clouds form dark, stubborn companions. And as it races through the solar system, shedding fragments of its alien past, it leaves us with both data and wonder. 3I Atlas may one day fade from sight, returning to the darkness between stars. But the record of its coma and dust behavior will remain, a case study in how nature continues to surprise us. It is not just another comet, it is a messenger carrying whispers of another sun, its activity a script written in gas and dust for us to interpret. And in that script, the rules of what comets can and cannot do are being rewritten before our very eyes. Composition Insights from JWST. When astronomers pointed the James Webb Space Telescope toward 3I Atlas, they knew they were looking at a once-in-a-generation opportunity. Only 2 other interstellar visitors had ever been detected before, and never had humanity been able to bring to bear such an advanced tool for probing their secrets. Webb's infrared spectrographs, designed to detect faint molecular signatures across space, promise to reveal the very recipe of this wandering fragment from another star system. What they found was not just interesting, it was startling. The JWST's first spectra of 3I Atlas showed a fingerprint unlike any comet previously studied. The coma glowed with strong absorption lines from carbon dioxide, dwarfing the presence of water vapor. On Earth and in most solar system comets, water is the main player. CO2 appears, but it rarely dominates. In 3I Atlas, however, the balance was inverted. The CO2 to H2O ratio was among the highest ever measured in any comet. This was the first major clue that the chemistry of its birth system was fundamentally different from ours. Perhaps it formed in a disk colder or more distant from its star than the birthplace of our own comets, where water was permanently frozen out, but carbon dioxide remained volatile enough to escape. The detection carried deep implications. If CO2 dominated, then the comet's structure likely contained thick layers of dry ice interspersed with darker, carbon-rich grains. This alone could explain some of the odd scattering effects seen in polarimetric studies. Carbon dioxide frost can coat dust particles, changing the way they bend and reflect light. It might also help explain the mysterious swarm appearance. Instead of bright, glistening water ice scattering sunlight, the dust clouds of 3I Atlas were cloaked in darkness, absorbing light like a shroud. Beyond the simple CO2 signal, Webb revealed traces of more complex carbon-bearing compounds. Preliminary analyses pointed to signatures consistent with carbon monoxide, formaldehyde, and even hints of larger hydrocarbons. These molecules are the building blocks of organic chemistry. Their presence did not prove life, far from it, but they added weight to panspermia theories, suggesting that comets serve as delivery systems for life's ingredients across the cosmos. If 3I Atlas carried such molecules, it meant that alien star systems were producing the same raw materials as ours. Life, at least in its chemical precursors, might be universal. But Webb's findings also raised contradictions. For decades, planetary scientists assumed that comets from other systems would look roughly like ours. After all, physics and chemistry are universal, yet here was a body flaunting ratios that strained those expectations. One explanation proposed was radial mixing in its home star's protoplanetary disk. Perhaps 3I Atlas had formed in a chaotic region where ices from near and far mingled, producing unusual chemistry. Another idea was that it originated around a low-mass red dwarf star, where stellar winds and radiation differ drastically from our sun's, influencing what ices can condense. Webb also contributed insights into the comet's dust. By examining the mid-infrared thermal emission, astronomers inferred grain sizes and compositions. Many of the particles were larger than those seen in typical solar system comets, some nearly pebble-sized, coated in dark carbon. Such clumps could explain the strange shadows drifting near the comet, the supposed dark swarm. If the grains clustered and resisted dispersal, they would appear as distinct companions rather than a diffuse cloud. Again, the details aligned with speculation that 3I Atlas wasn't just another comet, but an interstellar archive of alien chemistry. Perhaps most intriguing was the absence of certain molecules. In solar system comets, water dominates, but we also detect ammonia, methane, and a range of nitrogen-bearing compounds. In 3I Atlas, the nitrogen lines were weak to non-existent. That absence told a story. It suggested the comet formed in an environment depleted of nitrogen, another hint at its alien origin. Each missing molecule was as informative as each presence, painting a picture of a nursery star system with different priorities of chemistry. This chemical map sparked heated debate. Some researchers argued it proved that planetary systems across the galaxy produce wildly varied comets. Others cautioned that with a sample size of 3 interstellar visitors, it was far too early to generalize. Still, the evidence was clear. 3 Atlas was not like Borisov, nor like the comets of our Kuiper belt. It was its own creature, and Webb had laid bare its strangeness. Beyond pure science, the results fueled speculation that pushed into the cultural imagination. If a comet can be so chemically exotic, could it also carry clues of artificial manipulation? Supporters of the alien probe hypothesis pointed to the sunward plume and the odd swarm. Combined with the unusual chemistry, they claimed, these features might indicate deliberate engineering. Could the ratios of gases be tuned for propulsion? Could the dark grains act as shielding material? Most astronomers dismissed these ideas, noting that natural processes offered simpler explanations. Yet the Webb data gave just enough room for speculation to thrive. One avenue of speculation leaned toward planetary habitability. The dominance of carbon dioxide meant that if such a comet crashed into a terrestrial planet, it would deliver vast amounts of greenhouse gas. This could, in theory, warm a cold world, nudging it closer to habitability. Was this simply a coincidence of chemistry, or could it tie into ancient myths of star stones sent to prepare barren planets? Some cultural historians noted eerie parallels between Webb's data and old prophecies of celestial objects that would breathe fire into worlds. Science and legend found themselves once again in quiet dialogue. Meanwhile, the technical implications thrilled scientists. By analyzing Webb's spectra, they could estimate the comet's thermal properties, learning how efficiently it absorbed and re-emitted sunlight. They found it unusually dark with a low albedo, absorbing most of the radiation it encountered. This too fit with the idea of carbon-rich grains dominating its surface. It also explained why it appeared shadowy compared to other comets. Its darkness wasn't just metaphorical, it was literal, baked into its very composition. As the comet approached perihelion, the time of its closest approach to the Sun, Webb continued to watch. Scientists hoped to see how the CO2 and other volatiles changed under intense heating. Would water finally dominate as deeper layers thawed, or would carbon dioxide continue to rule? Each data point added a page to the growing story. Early signs suggested that even under stronger sunlight, the unusual ratios persisted. 3I Atlas seemed stubborn, unwilling to behave like any comet we knew. Ultimately, the insights from JWST transformed 3I Atlas from a mysterious dot in the sky into a chemical narrative. It was a narrative of carbon dioxide dominance, of organics scattered among alien dust, of nitrogen scarcity, of darkness both literal and symbolic. Through infrared eyes, Webb gave humanity its clearest look yet at the diversity of interstellar wanderers. It proved that our solar system is not a perfect template for the galaxy, but just one expression of countless chemical possibilities. And perhaps most importantly, Webb reminded us of perspective. For billions of years, fragments like 3I Atlas have likely drifted unseen through our skies, unnoticed and unmeasured. Only now, with technology advanced enough, can we peel back their layers and glimpse the alien recipes they carry. Each molecule detected by Webb is a word in a universal language of chemistry, a language spoken across stars. With 3I Atlas, we are just beginning to learn the dialects. The mystery, of course, is far from solved. Why does it carry so much carbon dioxide? Why are its dust grains so large and dark? Why does it lack nitrogen? Each answer leads to another question. But thanks to JWST, the questions are sharper, grounded in data rather than speculation. And as long as the comet remains visible, Webb will continue to read its chemical story, translating whispers from another star system into knowledge that will echo long after 3 Atlas has vanished back into the void. polarimetry, and surface dust grain clues. The story of 3I Atlas did not end with spectroscopy alone. While the James Webb Space Telescope revealed its unusual chemical composition, another set of tools, polarimetric observations, unlocked a different dimension of understanding. Polarimetry is not about what molecules are present, but about how light interacts with surfaces and grains of dust. By measuring the polarization of scattered sunlight, astronomers can infer the size, structure, and texture of particles too small and distant to ever capture directly. With 3I Atlas, the results were anything but ordinary. Normally, comets within our solar system exhibit a fairly predictable polarization curve. When sunlight bounces off their dust grains, the scattered light becomes polarized to a certain degree, and this polarization changes depending on the viewing angle. Most comets show a shallow negative polarization branch at small phase angles, meaning that under certain conditions, the light waves are aligned in ways that make the dust appear slightly darker. But with 3I Atlas, polarimetry revealed something deeper and more pronounced. Its negative polarization was unusually strong, sharper than almost any comet previously studied. That simple measurement spoke volumes about its surface and the grains billowing from its nucleus. The implication was clear. The dust around 3I Atlas was not the fluffy, porous mixture of ice and silicates familiar from comets like Halley or Hale-Bopp. Instead, it appeared to be darker, denser, and possibly coated with carbon-rich material. Some grains may have been compact rather than porous, their crystalline structures bending light in exotic ways. Others may have been layered, ice cores wrapped in carbon or silicate shells, or vice versa. Such layered structures are rarely observed in solar system comets, but they can occur under different conditions of formation. For 3I Atlas, it suggested a birthplace in a protoplanetary disk with chemical and thermal gradients unlike our own. The surface of the nucleus, too, could be inferred indirectly. A strong negative polarization branch often indicates a coating of fine, dark material. In other words, the nucleus of 3I Atlas might be cloaked in soot-like dust, absorbing sunlight rather than reflecting it. This fit with its low albedo. Astronomers noted that it was darker than most comets, absorbing far more light than it returned. In space, darkness often signals a high content of organic-rich compounds, sometimes called tholins, formed by radiation acting on carbon-bearing ices. If 3I's Atlas carried such materials, then it was not just a visitor from another star system, but a messenger bearing chemical relics that may resemble the seeds of life. Polarimetry also shed light, quite literally, on the swarm debate. If the coma contained large clumps of dark, carbon-rich grains, their scattering behavior could make them appear as distinct objects, even when they were just denser pockets of dust. Under certain angles, such clumps could masquerade as shadowy companions orbiting the nucleus. In this way, polarimetric data provided a natural explanation for some of the more mysterious observations. But it didn't close the case entirely. The clumps still seemed unusually stable, and the negative polarization only underscored that the grains were exotic. This meant that while polarimetry explained part of the story, it also confirmed that 3I Atlas was different enough to warrant continued suspicion. Another striking clue came from the grain size distribution. Polarimetric measurements combined with thermal emission data suggested that the dust contained an unusually high fraction of larger grains, some nearly pebble-sized. Most comets release fine dust, creating a diffuse and reflective coma, but larger grains scatter light differently, often producing darker halos and strange polarization signals. If 3I Atlas shed such bouldery fragments, it would naturally appear more shadowy, feeding into the swarm illusion. More importantly, large grains would resist solar radiation pressure, allowing them to linger near the nucleus rather than dispersing rapidly. That, too, could help explain why companions seem to hang close instead of trailing off into a tail. The presence of large dark grains tied directly into theories of comet origin. In the early days of a planetary system, dust grains stick together, forming pebbles, then rocks, then planetesimals. If 3I Atlas is ejecting such pebbles, it may be preserving the earliest building blocks of its home system. These are not just grains of dust. They are fossilized records of planet formation around another star. Each particle carries within it a story of chemistry, radiation, and time. Polarimetry allowed scientists to read that story, even if imperfectly. Some researchers took the findings even further. The pronounced negative polarization suggested complex internal structures in the grains, perhaps multiple layers or voids. This could indicate that 3I Atlas's dust had undergone cycles of heating and freezing, perhaps as it passed close to its parent star long ago before being ejected into interstellar space. In that sense, the dust wasn't just exotic, it was seasoned, bearing scars of a journey spanning millions or even billions of years. If so, then 3I Atlas is more than a comet. It is a time capsule carrying the weathered remains of an alien system's history. The connection to panspermia theories was inevitable. Large, carbon-rich grains protected by dark coatings are excellent shields against radiation. If microscopic life or prebiotic molecules were ever embedded within them, such grains could preserve that chemistry during long interstellar voyages. Though speculative, some scientists couldn't resist pointing out that 3I Atlas's dust was precisely the kind of medium envisioned in theories of life's cosmic spread. If dust from such comets can travel between stars, then the building blocks of life might not be limited to one solar system, but shared across the galaxy. Yet the polarimetric data also highlighted gaps in our knowledge. Models of light scattering often rely on solar system comets, and applying them to interstellar material stretches assumptions. Are the grains truly compact, or are we misinterpreting exotic structures? Is the darkness due to organics, or could it stem from minerals we rarely see in our comets? Each interpretation remains provisional, awaiting more data. But the very fact that 3I Atlas challenges these models is itself invaluable. It forces scientists to expand their frameworks, to consider broader possibilities of chemistry and structure. Beyond the scientific community, the polarimetric results fed public intrigue. News outlets reported that the comet was darker than coal, its dust shadowy companions drifting around it. These dramatic phrases captured imagination, painting 3I Atlas as a ghostly traveler cloaked in mystery. Online forums speculated that the strange polarization was evidence of artificial materials, perhaps metallic coatings or engineered structures. Though most scientists dismissed such claims, they acknowledged that the data left room for wonder. The truth, after all, was still being pieced together. What stands out most is how complementary polarimetry proved to spectroscopy. Spectroscopy told us what 3I Atlas is made of: carbon dioxide, carbon monoxide, organics. Polarimetry told us how those ingredients were arranged into large, dark, layered grains that scatter light in alien ways. Together, these tools painted a richer portrait. They revealed a comet whose dust is both familiar and foreign, echoing our own comets while diverging in key details. It was not just a chemical anomaly, but a structural one, a reminder that the diversity of the cosmos extends down to the tiniest grains of dust. As 3I Atlas continues its journey through the solar system, polarimetric monitoring remains vital. The polarization signals may change as the comet nears the sun, as different layers of ice and dust erupt from beneath its surface. If the signals weaken, it may mean the outer dark coating has been stripped away. If they strengthen, it could suggest even stranger materials lurking deeper within. Each shift will add to the puzzle and perhaps bring us closer to understanding how this interstellar visitor was forged. For now, though, one conclusion is clear. 3I Atlas is not like the comets we grew up with. Its dust is darker, its grains are larger, its scattering is stranger. Polarimetry has revealed a cloak of mystery woven from alien chemistry, a swarm of shadows drifting around a nucleus forged under another sun. In those shadows may lie answers not just about this comet, but about the countless worlds that litter our galaxy. And until those answers arrive, the polarized light from 3I Atlas will continue to whisper across the void, telling us that the universe still holds surprises in even its smallest specks of dust. Size, mass, and uncertainties. When astronomers first turned their instruments on 3I Atlas, one of the most pressing questions was deceptively simple: how big is it? Determining the size and mass of a distant interstellar comet might sound straightforward, but in reality, it is one of the most difficult problems in observational astronomy. Unlike planets or moons, comets are small, irregular, and wrapped in glowing halos of dust and gas that make their true boundaries invisible. With 3I Atlas, these challenges multiplied. Its interstellar trajectory gave astronomers only a brief window of observation, and its strange activity muddied the estimates further. The result is that the size and mass of 3I Atlas remain surrounded by uncertainties that are as fascinating as they are frustrating. Initial attempts to measure its size came from brightness. Astronomers measured the total light reflected by the comet and compared it to models of albedo, how reflective its surface might be. If the comet was dark, like many solar system comets coated in soot-like material, then it had to be larger to reflect the observed amount of light. If it was more reflective, then it could be smaller. Early data from the Hubble Space Telescope placed a wide range on its nucleus, somewhere between about 160 meters and 2.8 kilometers in radius. That range translates into more than an order of magnitude difference in surface area and an even larger difference in volume and mass. This uncertainty is not unusual for a new comet, but what made 3I Atlas remarkable was that even as more data came in, the range remained stubbornly wide. Part of the problem came from its coma. The halo of dust surrounding the nucleus made it difficult to separate the light from the solid body itself. Some models suggested that the nucleus was relatively small, perhaps only a few hundred meters across, and that its brightness came largely from the outpouring of gas and dust. Others leaned toward a larger body hidden within, with the activity merely accentuating its glow. Mass estimates only deepened the mystery. In August 2025, reports emerged suggesting that 3I Atlas might be anomalously massive for an object of its size. Some calculations placed its mass above 30 billion tons. For context, this would make it heavier than many comets of similar apparent brightness. How could such a small, faint visitor carry so much weight? One possibility was density. If 3I Atlas had an unusually compact, rocky interior, rather than the fluffy, porous structure common in comets, it could pack more mass into less volume. Another possibility was error. The methods for estimating its mass relied on indirect assumptions, such as how fast material was being expelled, and small errors in those assumptions could inflate the results. The density debate struck at the heart of comet science. Most solar system comets are loosely bound dirty snowballs with densities lower than water, often as little as 0.5 grams per cubic centimeter. But if 3I Atlas really was as massive as some reports suggested, its density could be 2 or 3 times that, more like solid rock. Such a discovery would challenge our understanding of how comets form, not just here, but across the galaxy. Was this object an icy body hardened by eons of radiation? Or was it perhaps misclassified, a fragment of an asteroid-like body flung from another star system? Another complicating factor was the unusual activity of 3I Atlas. Its strong carbon dioxide outgassing and sunward plume meant that its coma was brighter and stranger than most. This made it especially difficult to isolate the nucleus. Astronomers attempted to model the jets and subtract their contribution, but the plume was unpredictable, sometimes flaring, sometimes dimming. Every flare risked making the nucleus appear larger or smaller than it really was. To add to the confusion, estimates of the dust grains surrounding 3I Atlas suggested that many of them were large, perhaps pebble-sized or bigger. If these grains clustered near the nucleus, they could artificially inflate brightness measurements, making the comet look larger than it truly was. Some researchers speculated that the swarm of dark objects reported near the comet might in fact be these large grains, lingering close enough to fool calculations. If true, then the nucleus itself might be at the smaller end of estimates, while the extra companions added to the illusion of bulk. But what if the larger estimate was correct, and 3I Atlas really was several kilometers across? In that case, its mass could indeed be staggering. A body of that size and density would exert enough gravity to influence the behavior of nearby fragments, perhaps explaining why the swarm appeared stable. In this sense, the uncertainty about its size tied directly into the mystery of its companions. A larger nucleus could shepherd fragments, a smaller one could not. Until astronomers pinned down the truth, both possibilities remained on the table. The uncertainty also extended to shape. With Oumuamua, elongated shape became a central debate. Was it a cigar, a pancake, or something else entirely? With 3I Atlas, shape was harder to discern because the coma obscured direct imaging. Some speculated that it could be irregular, perhaps flattened or elongated, which would affect how it reflected light and further complicate size estimates. Others propose that it might be closer to spherical, but until spacecraft or high-resolution occultation events provided sharper data, the question remained unresolved. The practical consequences of these uncertainties are profound. If 3I Atlas is small and light, it is merely another cometary oddity, interesting but not exceptional. If it is large and massive, then it may represent a new class of interstellar object, one capable of carrying with it not just dust and gas, but an entire ecosystem of fragments, clumps, and perhaps even frozen oceans within. The difference between a nucleus of a few hundred meters and one of several kilometers is the difference between a cosmic pebble and a cosmic mountain. These uncertainties also highlight how little we know about the population of interstellar objects. With only 3 confirmed visitors, Oumuamua, Borisov, and Atlas, the sample size is far too small to define norms. Borisov was large, bright, and very comet-like. Oumuamua was small, faint, and unlike anything we'd seen. Atlas appears to fall somewhere in between, but carries mysteries of its own. If future surveys reveal more, patterns may emerge. Until then, every estimate of size and mass remains provisional, another piece of an unfinished puzzle. The limits of our technology are part of the story. Even with the Hubble Space Telescope, the James Webb, and some of the world's most powerful ground-based observatories, astronomers are still working at the edge of their instruments' capabilities. 3I Atlas is small, fast, and fleeting. It will not linger in the solar system for long. Each observation comes with caveats, assumptions, and margins of error. Every claim of size or mass must be accompanied by humility. We are peering at a distant traveler through keyholes in the sky. And yet, even uncertainty is valuable. The very fact that estimates vary so widely is a reminder of the comet's uniqueness. Its brightness does not match its activity. Its activity does not match its presumed size. Its mass does not match its apparent fragility. Each mismatch forces scientists to refine their models, to reconsider what interstellar objects can be. Perhaps some are porous and fluffy, others dense and rocky. Perhaps the diversity is greater than we ever imagined. In popular culture, these uncertainties have fueled speculation. A massive nucleus supports the idea of a mothership shepherding smaller craft. A smaller nucleus surrounded by a swarm suggests artificial satellites escorting a probe. Though most scientists dismiss such interpretations, the ambiguity leaves room for imagination to flourish. In the absence of certainty, stories grow, and 3I Atlas has become fertile ground for both science and speculation alike. Ultimately, the truth about its size and mass may never be fully resolved. Without a dedicated mission, we may never see the nucleus directly. By the time models converge, the comet will be gone, fading into the black between stars. But even then, the uncertainty itself will remain valuable. It reminds us that the universe is not neat, not predictable, not fully within our grasp. Sometimes the most important discoveries are not definitive answers, but the realization that the questions are bigger than we thought. So when astronomers ask, how big is 3I Atlas? The real answer may be large enough to reshape our understanding, massive enough to challenge our assumptions, and uncertain enough to keep us watching. In that sense, its size and mass are not just numbers to be measured. They are mysteries to be lived with, enigmas that expand the horizon of what an interstellar visitor can be. Origin hypotheses and age. Every interstellar object carries with it a question that is both scientific and philosophical. Where did it come from, and how long has it been traveling? With 3I Atlas, that question looms larger than ever. Its chemistry, its activity, its swarm-like surroundings, none of these can be fully understood without tracing its origins. And while astronomers cannot point to a single star with absolute certainty, they can use physics, orbital mechanics, and models of planetary system formation to sketch a series of possibilities. The results are both illuminating and humbling, reminding us just how vast and ancient the galaxy truly is. The first clue to origin lies in its trajectory. When 3I Atlas was discovered, orbital calculations quickly showed that it was not bound to the Sun. Its eccentricity was greater than 1, placing it firmly on a hyperbolic path. That hyperbolic shape means it did not form here. It entered our solar system from interstellar space and will exit again once its brief encounter with the Sun is complete. By running its orbit backward through time, astronomers could determine the direction it came from. This kind of analysis is tricky because small uncertainties in position magnify over millions of years of travel. Still, broad strokes emerged. 3I Atlas appears to have come from a region near the constellation Serpens, crossing interstellar distances before intersecting with our neighborhood. The sheer velocity of the object is another hint. At discovery, it was moving at nearly 26 kilometers per second relative to the Sun, faster than most bound solar system bodies, but consistent with the escape speeds expected of ejected debris from other stars. In planetary formation, gravitational interactions can fling icy planetesimals outward. When giant planets form and migrate, they scatter comets and asteroids like billiard balls. Most remain bound to their host star's Oort cloud. A few, however, are thrown hard enough to escape completely. 3I Atlas is almost certainly one of these refugees, cast out of its birth system millions or billions of years ago. Its chemistry adds weight to the story. The dominance of carbon dioxide over water vapor suggests it formed in a region colder than the zones where our comets originated. In our solar system, comets are mostly water ice rich, with CO2 and CO as secondary players. For 3I Atlas, the balance was reversed. This hints at a birth environment far from a host star, perhaps in the outer reaches of a disk where temperatures plunged low enough that water froze rock solid, locked away, while carbon dioxide remained volatile. Alternatively, it may have formed around a different kind of star altogether. Red dwarfs, for instance, emit different patterns of radiation that could shape comet chemistry in ways unfamiliar to us. Age is harder to pin down, but equally fascinating. Interstellar objects travel at immense speeds, but even so, crossing from one star system to another takes millions of years. If 3I Atlas was ejected early in its home system's history, it could have wandered the galaxy for billions of years before encountering ours. Its surface, battered by cosmic rays, would carry the scars of that long journey. Radiation tends to darken ices, turning them into tar-like organics. That could explain the unusually low reflectivity and the dark dust grains revealed by polarimetry. In this sense, the comet is both ancient and altered, an original fragment of alien creation, weathered by eons of interstellar exposure. Some models suggest that the galaxy could be filled with objects like this, trillions of interstellar comets drifting unseen between stars. Most will never be detected. Only those that happen to cross paths with our sun at the right angle and brightness can be spotted. The fact that 3I Atlas is only the third confirmed interstellar object hints at how rare our chances of study are. Yet, ironically, its very discovery suggests these wanderers may be common. If we've found 3 in less than a decade, perhaps the void is littered with them, silent travelers from countless planetary nurseries. Theories of panspermia tie directly into origin and age. If comets can travel between stars, carrying with them organics or even microbial life shielded within large grains of ice, then life itself might not be confined to one system. 3I Atlas, with its carbon-rich chemistry and dark protective dust, could be a perfect vehicle for such transfer. Imagine a tiny microbe frozen billions of years ago in a distant star system, carried across light years by this comet, only to be released in another planetary system ages later. The sheer timescales make such a scenario improbable but not impossible. The chemistry Webb detected, formaldehyde, hydrocarbons, organics, feeds directly into this speculation. Its origin story may not just be about where it was born, but about what it carried across the galaxy. Yet for all the fascination, the uncertainties remain daunting. Backtracking its orbit to a specific star system is nearly impossible. Over millions of years, gravitational nudges from passing stars and galactic tides alter trajectories. Even if astronomers could run the numbers backward, the precision would collapse after only a few million years. At best, they can point to regions of the sky, broad swaths where the comet might have originated. Some studies suggested it could have passed near the star systems of Serpens or Hercules tens of millions of years ago, but these are educated guesses. For all we know, its birthplace might remain forever hidden, its true star long moved on from the location it once occupied. Another question lingers. When exactly was it ejected? Did 3I Atlas leave its home system during the violent youth of star and planet formation when gravitational chaos reigned? Or did it escape later, perhaps after billions of years of quiet orbit thrown out by some late instability. If it was ejected early, its age as a wanderer could be nearly as old as the star it formed around. If it was ejected late, it might have spent billions of years circling a star before being set free. Both scenarios fit the data. The darkness of its surface points to immense time in interstellar space, but how much time remains a mystery? Even its survival raises questions. Objects traveling between stars face harsh conditions: cosmic radiation, micrometeorite impacts, thermal cycling in interstellar voids. Many should disintegrate over such spans. That 3I Atlas remains intact suggests it is sturdy, perhaps more so than typical comets. Its mass estimates, possibly anomalously high, may reflect this strength. Could its resilience tell us something about the durability of material forged around other stars? If so, its survival is part of its origin story, a testament to the toughness of alien matter. Speculation goes further still. Some theorists, echoing ideas floated during the Oumuamua debates, wonder if interstellar comets like 3I Atlas could sometimes be artificial. Its odd plume, its swarm of companions, its unusual chemistry, could these be the hallmarks of engineered craft rather than natural debris? While mainstream science leans toward natural explanations, the hypothesis persists in the public imagination. If it were artificial, its origin would not random planetary system, but a civilization, its age not billions of years, but however long ago it was launched. That idea may be unlikely, but it underscores the profound mystery of tracing origins across cosmic gulfs. In the end, the origin hypotheses converge on a simple truth. 3I Atlas was born under another sun long ago and has spent untold ages wandering the galaxy. Its chemistry speaks of a colder nursery, its darkness of long exposure, its orbit of violent ejection. Whether it came from a red dwarf system, a sun-like star, or somewhere stranger, we may never know. Whether it has drifted for millions or billions of years, we cannot yet say. But what is certain is that it is older than any human civilization, older than Earth's continents, older perhaps than life itself on our planet. That age humbles us. As we watch 3I Atlas streak across the sky shedding dust and secrets, we are witnessing a relic not just of another place, but of another time. Its story began long before ours, and it will continue long after, fading into the dark once more. To study it is to glimpse across deep time and space, to trace a thread from a distant star system to our own. And though uncertainties remain, they are part of the beauty. For in the uncertainty lies the reminder that the universe is vast, ancient, and still full of mysteries waiting to be uncovered. Speculation and controversy, alien probe theory. From the moment astronomers realized that 3 Atlas was not bound to the sun, but instead passing through our solar system from the stars beyond, the imagination of the public and even some scientists leapt ahead of the data. The memory of Oumuamua, the first interstellar object discovered in 2017, was still fresh. That elongated visitor sparked debates that reached far beyond astronomy, with respected astrophysicist Avi Loeb famously suggesting that it could have been an alien probe, an artifact of a distant civilization. So when 3I Atlas arrived in 2025, the stage was already set. It didn't take long for whispers of mothership, engineered object, and alien technology to enter the conversation. The idea might sound outlandish, but speculation thrives when mysteries multiply. With 3I Atlas, the mysteries were everywhere. Its coma was dominated by carbon dioxide rather than water vapor. It exhibited a sunward plume, streaming material in the wrong direction against the solar wind. Polarimetric studies showed dark, unusual grains unlike those seen in solar system comets. And most tantalizing of all, some images appeared to show a swarm of dark companions drifting around it, stable and shadowy like an escort. Put all of these anomalies together, and the question practically asked itself, could 3I Atlas be something more than a natural rock and ice fragment? The alien probe regained its first traction online. Social media platforms amplified images and amateur observations, often without context. Posts claimed that the swarm was a fleet of smaller craft accompanying a mothership. Others suggested that the plume was evidence of propulsion, not natural outgassing. In a digital echo chamber primed by years of UFO debates and government disclosures, the story caught fire. Before long, headlines began appearing in fringe outlets. Astronomers baffled by alien comet, or Three-Eye Atlas, proof of visitors from the stars. But beyond the hype, some serious thinkers also entertained the possibility, not as a conclusion, but as a hypothesis. Avi Loeb himself, never one to shy away from controversy, commented that it would be unwise to dismiss artificial origins outright. His reasoning echoed what he had argued about Oumuamua. When something looks unlike anything we have seen before, we should be open to extraordinary explanations. Loeb pointed to the swarm as especially interesting. Natural debris should disperse, not hover. If the companions remain stable, it could suggest artificial station keeping. Critics countered that the data was far too uncertain to support such claims, but the controversy only deepened. For mainstream astronomers, the alien probe theory is both frustrating and oddly useful. On the one hand, it distracts from serious science. Each time an interstellar object is discovered, conspiracy theories bloom, and scientists are forced to spend time debunking rather than studying. On the other hand, the public fascination drives interest and funding. Telescopes are pointed at these objects because the public demands answers. In this way, speculation keeps interstellar research in the spotlight. The debate often centers on plausibility. If Three-Eye Atlas were artificial, what would it mean? One scenario imagines it as a probe sent deliberately by another civilization. Perhaps it is an ancient relic, long since inactive, drifting aimlessly after its creators perished. Perhaps it is still active, silently observing as it passes through our system. Another scenario imagines it as part of a larger program, swarms of probes seeded through the galaxy to gather data. In such a model, the swarm seen around it might not be debris at all, but a fleet of smaller devices. Skeptics raise immediate objections. First, the data we have can be explained naturally. The swarm may be clumps of dust. The plume may be unusual outgassing. The dark grains may simply reflect chemistry from another system. Occam's razor, the principle that the simplest explanation is usually correct, suggests that extraordinary claims are unnecessary. Second, the alien probe theory requires assumptions about civilizations we have no evidence for. Why would they build comets as probes? Why would they send them without detectable signals? If the goal were observation, why make the object so faint and difficult to detect? Yet proponents of the idea counter with equally strong rhetorical questions. Why assume that alien engineering would resemble our own? If a civilization millions of years older than ours wanted to explore the galaxy, wouldn't hiding probes in comet-like disguises be clever? Why broadcast signals when passive observation would be safer? And if trillions of comets exist in the galaxy, why not use them as ready-made vessels, hollowing out or modifying natural bodies to carry instruments? In that light, Three-Eye Atlas would not be an outlier, but an example of a larger, hidden phenomenon. The controversy is sharpened by timing. Three-Eye Atlas was discovered just as public discourse about extraterrestrial life was heating up. Government reports on unidentified aerial phenomena had been released. Space agencies were intensifying the search for biosignatures on Mars and exoplanets. In that climate, every anomaly seemed like potential evidence. The alien probe theory fit neatly into the cultural moment, whether scientists welcomed it or not. Scientific papers on Three-Eye Atlas generally avoid the term alien. Instead, they focus on describing anomalies and proposing natural mechanisms. But the language is often cautious. Phrases like poorly understood physics or unprecedented behavior leave gaps where speculation grows. The gap between data and certainty is the crack where controversy seeps in. And once the public seizes on a story, scientists can do little to control it. In some ways, the debate echoes earlier eras of astronomy. When comets streaked across the skies of medieval Europe, they were seen as omens, signs of divine intervention. Today, with more data but the same human imagination, they are seen as potential alien messengers. The symbols have changed, but the impulse remains, to find meaning in the unexplained. Three-Eye Atlas, with its swarm and plume, has become a new canvas for these ancient instincts. What makes the alien probe theory so persistent is not that it is the strongest explanation, but that it is the most compelling. Natural processes can be complex and messy, but they often fail to capture the imagination. Saying it's just dust behaving oddly does not inspire wonder. Saying it might be an alien probe does. Even if the former is more likely, the latter keeps people engaged. For scientists, the challenge is to harness that engagement without letting speculation overshadow evidence. As the comet continues its journey, the controversy will not vanish. If the swarm disperses and the plume fades, natural explanations will gain strength. If the anomalies persist, speculation will only intensify. Either way, the story of 3 Atlas will remain a case study in how science and imagination interact. It is a reminder that astronomy is not just about data points, but about narratives. And those narratives are shaped as much by culture as by telescopes. In the end, the alien probe theory says less about 3 Atlas than it does about us. It reflects our yearning for connection, our fear of being alone, and our habit of turning the unknown into a mirror of our hopes and anxieties. Whether the comet is nothing more than a frozen relic or something engineered, it has already served as a probe of another kind, a probe into the human imagination. And perhaps that is the most fitting legacy. If 3 Atlas teaches us anything, it is that the cosmos is still capable of surprising us, still capable of sparking debates that blur the line between science and speculation. The controversy itself ensures that this interstellar visitor will not be forgotten. Whether alien or natural, it has fulfilled the role of a true cosmic messenger, not by delivering answers, but by inspiring questions that reach as far as the stars it came from. Could the swarm be technology or structures? When images of 3I Atlas began circulating online, showing faint shadows or clumps seemingly moving with the interstellar comet, the phrase swarm of dark objects quickly took root. For many, the word swarm carried implications far beyond natural debris. Could these companions be more than rocks or dust? Could they be technology, devices, or structures placed intentionally around the object? It was a question that echoed the wildest speculation around Oumuamua years before, but this time with an even stranger set of anomalies to stoke the fire. The leap from natural fragments to artificial structures may sound extreme, but in the culture of 21st century astronomy, it is almost inevitable. For decades, humanity has imagined what alien engineering might look like. Science fiction has given us Dyson spheres, generation ships, and self-replicating probes. Scientists themselves have speculated about von Neumann machines, self-sustaining robotic explorers that could spread across a galaxy in exponential numbers. If such devices exist, how might they travel? Some argue that hiding them in comet-like bodies would be efficient and stealthy. A natural-looking shell could disguise technological interiors. To the casual telescope, they would look like just another frozen rock, until a closer look revealed anomalies. In this context, the idea that 3I Atlas might be carrying structures is not entirely dismissed by enthusiasts. The swarm of dark companions has been interpreted as possible probes or modules loosely accompanying a central mothership. Their dark appearance would make sense if they were designed to absorb energy or shield themselves from radiation. Their apparent stability near the nucleus, rather than dispersing like ordinary debris, raises eyebrows. Could they be in formation rather than random scattering? Could invisible forces, electromagnetic fields, or controlled propulsion be keeping them in place? For those who entertain the theory, parallels are drawn with known human technologies. Satellites today often fly in formations, sharing tasks while maintaining positions relative to one another. Swarms of drones have been tested on Earth to cover large areas with flexibility. By analogy, a sufficiently advanced civilization might employ swarms of autonomous probes to explore distant systems. Each could gather data, communicate with its companions, or perform specialized functions. In that sense, 3I Atlas would not just be one visitor, but many, an expedition disguised as a comet. But skeptics offer counterpoints just as quickly. First, there is the problem of evidence. Most of the companions could be explained as clumps of dust. Cometary outgassing is messy, and jets can create uneven streams that mimic structure. Polarimetric studies suggest that 3I Atlas produces unusually large, dark grains, pebble-sized or bigger. These grains resist dispersal, making them appear to hover. What looks like technology may simply be alien chemistry at work. Second, there is the issue of motivation. Why would a civilization send probes disguised as comets? Wouldn't it be simpler to send stealthy spacecraft directly? Unless some counter, the disguise is the point. After all, comets are ubiquitous. If one wanted to explore without drawing attention, hitching a ride inside something ordinary might be the perfect tactic. Speculation stretches further when considering the plume of 3I Atlas. The stream of material pointing sunward, opposite to what physics predicts, has been interpreted as possible propulsion. If the swarm were technological, could the plume be exhaust? Could the smaller companions be modules adjusting their positions relative to the central body? Such ideas are difficult to prove, but the coincidences fuel debate. Every anomaly seems to add another brick to the wall of speculation. There is also the question of scale. If the nucleus of 3I High Atlas is closer to 3 kilometers across, then any artificial structures near it would be dwarfed, invisible at our current resolution. Even so, swarms of 100-meter objects would be too small for most telescopes to detect clearly, appearing only as shadows or irregularities in brightness. This uncertainty leaves a wide open space for speculation. Without definitive data, imaginations rush to fill the void. Supporters of the technology theory sometimes point to human history. Our own species is on the verge of interstellar exploration. Proposals like Breakthrough Starshot aim to send tiny probes propelled by light sails toward Alpha Centauri. If humanity is already envisioning swarms of lightweight, mass-produced spacecraft, why wouldn't older civilizations have done the same? If they had millions of years to work with, such swarms could have spread throughout the galaxy, embedded in comet-like carriers. From that perspective, encountering one near our sun would not be shocking, but expected. Mainstream astronomy, however, holds to natural explanations. The swarm, they argue, can be fully explained without invoking aliens. Large grains, clumped ejections, and perspective illusions account for the observations. The danger of assuming technology is that it shifts the focus from testable hypotheses to speculation. But even scientists acknowledge that they cannot yet rule out stranger possibilities. They simply prefer to exhaust natural explanations first. Controversy arises from the tone of certainty. When skeptics dismiss the idea outright, enthusiasts push back, arguing that science should remain open-minded. When enthusiasts declare the swarm a fleet of alien craft, scientists recoil, insisting that evidence must come before conclusions. In the middle lies the most reasonable ground. Acknowledge the anomalies, explore natural models, but do not close the door entirely on extraordinary hypotheses. The discussion also reveals something deeper about human psychology. The idea of alien structures excites us not because it is likely, but because it resonates with our desire for connection. To imagine 3I Atlas as a comet is fascinating. To imagine it as a disguised probe is electrifying. The swarm becomes not just dust, but a fleet, not just fragments, but devices with purpose. It transforms a cold rock into a story, a messenger from intelligent beings. That leap captures the imagination in ways natural models rarely do. Still, even the technological interpretation faces its own paradox. If the swarm were truly engineered, why would it be so ambiguous? Why not transmit signals or show clearer signs? Some suggest that subtlety is deliberate, that alien probes might be designed to avoid detection, to watch rather than announce. Others argue that if such probes exist, they may be derelict, drifting aimlessly after their creators are long gone. In that case, the swarm could be nothing more than abandoned relics, indistinguishable from debris except to the most careful eyes. At its core, the debate about whether the swarm could be technology or structures reflects a larger truth. The boundaries between science and imagination are porous when faced with the unknown. 3I Atlas presents anomalies that do not fit neatly into existing categories. Whether those anomalies are natural or artificial, they challenge our assumptions. And until better data arrives, perhaps from new telescopes or one day from a probe sent to intercept such visitors, the speculation will continue. What we know is that 3I Atlas is real, observable, and strange. Its swarm is not a rumor, but a description of unusual behavior around it. Whether that swarm is dust clumps, pebbles, or something more remains unsolved. The possibility of technology cannot be confirmed, but neither can it be completely denied. In this liminal space, the story thrives. The comet becomes a mirror, reflecting both our scientific rigor and our imaginative hopes. In the end, perhaps the true value of the swarm lies not in whether it is natural or artificial, but in the questions it forces us to ask. How would we recognize alien technology if it passed us by disguised as debris? What standards of evidence would convince us? And how can we remain open to extraordinary possibilities without leaping too quickly into fantasy? These questions linger as 3i Atlas continues its journey. If the swarm is dust, then it will eventually disperse, leaving only an academic puzzle. If it is technology, then it may remain stable, confounding us until the comet fades from view. Either way, the speculation has already accomplished something remarkable. It has pulled millions of eyes toward the sky, reminded us of the possibility of other minds, and shown that the unknown still has the power to unsettle and inspire. Whether nature or design, 3i Atlas has given us not just data, but a story. One written in shadows, carried across the stars, and whispered in the dark halo of a visitor from beyond. Alternative explanations. Fragments or dust clouds. For every spectacular theory about swarms of alien probes surrounding 3i Atlas, there are quieter, steadier voices insisting that the explanation may be simpler. The strange shadows and companions drifting near the comet could be nothing more exotic than fragments of the nucleus or clumps of dust. Cometary science, after all, is full of examples where debris behaves in ways that defy easy prediction. And while 3i Atlas has proven itself unusual in many respects, natural processes still provide the most grounded framework for understanding what we see. The first and most obvious possibility is fragmentation. Comets are fragile. They are not solid rocks, but loosely bound mixtures of ice, dust, and frozen gases, sometimes described as dirty snowballs. When such an object passes close to a star, its surface heats, volatile ices turn to gas, and the pressure can rip it apart. In our solar system, we have witnessed spectacular comet breakups. Comet Shoemaker-Levy 9, torn into a string of pearls by Jupiter's gravity in 1992, left a trail of fragments that eventually slammed into the giant planet. Comet 73P Schwarzmann-Wachmann 3 fragmented repeatedly in the early 2000s, shedding dozens of smaller bodies. More recently, Comet Atlas in 2020 disintegrated before reaching perihelion, scattering its remains across space. If such events are common among our comets, why not among interstellar ones? 3i Atlas, approaching the Sun after untold ages in deep freeze, could easily be cracking and shedding fragments. Each companion object seen around it might be a piece of its nucleus, broken away by stress. The sunward plume, so puzzling when interpreted as a jet, might even be linked to these breakups as internal pressure vents explosively from fractures. Yet the puzzle is not fragmentation itself, but the behavior of the fragments. Normally, once pieces break off, they follow diverging paths. Gravity, solar radiation, and momentum spread them apart. Over time, they line up in chains or scatter widely. But with 3i Atlas, observers claim the companions seem to linger, hovering near the nucleus. Why do they not disperse? That stability is what gives rise to talk of a swarm rather than a trail. One natural explanation is size. If the fragments are unusually large, hundreds of meters across, they would have enough inertia to resist rapid dispersal. They might remain near the nucleus for weeks or months, appearing to form a stable cluster. Another explanation involves geometry. If the fragments broke off at low velocities, they might simply be coasting alongside the nucleus, sharing its orbit rather than peeling away. From Earth's perspective, they could appear to hover, even if in reality they are slowly drifting apart. Dust clouds present another possibility. Instead of distinct solid bodies, the companions might be dense clumps of dust grains. Cometary outgassing often expels not just fine particles, but large aggregates, clusters of pebbles bound by electrostatic forces. Such clumps can scatter light differently than diffuse dust, appearing as dark shadows or blobs. If 3i Atlas is producing unusually large grains, as polarimetric studies suggest, then these clumps could masquerade as miniature moons. Their dark coloration, absorbing rather than reflecting light, would make them look especially mysterious. Electrostatics could play an even larger role. In the near vacuum of space, dust grains become electrically charged by solar radiation. Charged particles repel and attract one another in complex ways, sometimes forming temporary clusters. If the grains around 3i Atlas are coated with carbon or other exotic materials, their electrical behavior could be unlike anything we've seen in local comets. Instead of dispersing, they might cling together, maintaining clumps that orbit near the nucleus like shadowy satellites. Radiation pressure from the sun adds another layer of complexity. Normally, solar photons push dust outward, creating the classic comet tail. But the strength of this push depends on particle size. Small grains are blown away quickly, larger ones barely budge. If 3I Atlas is releasing a spectrum of grain sizes, we might see a mix of behaviors, fine dust streaming outward while larger clumps remain stubbornly close. This combination could create the illusion of a swarm, with scattered dark companions hovering around the main body, while fainter material trails behind. The unusual composition of 3I Atlas may amplify these effects. With carbon dioxide dominating its activity rather than water, the gas jets erupting from its surface may behave differently. CO2 sublimates at lower temperatures than water, meaning jets could activate earlier and in more distant regions of the comet. These jets may expel material in unusual directions or at unexpected speeds. The sunward plume, baffling when viewed as a propulsion-like effect, might simply be a CO2 jet angled inward by surface topography. If so, it could be releasing both gas and large dust clumps in patterns that mimic structured behavior. Historical parallels exist. Comet Encke, observed for centuries, occasionally produces dust trails that linger as dense clumps, leading to meteor showers on Earth. Comet Halley 2 has been recorded shedding large, dark grains that persist long after the comet has passed. These examples remind us that cometary behavior is varied and sometimes counterintuitive. 3I Atlas may not require alien engineering to explain its companions, only physics we do not yet fully understand in the interstellar context. Another natural explanation involves perspective. Telescopic images of faint objects are notoriously tricky. Long exposures can smear stars, background galaxies can overlap, and processing algorithms can create artifacts. What looks like a companion could sometimes be a chance alignment. With 3I Atlas, faint blobs near the nucleus may be noise, not bodies. Even professionals acknowledge this risk. Until multiple observatories confirm the same features, caution is warranted. The swarm might not be as large or as coherent as some claim. Still, even the most cautious astronomers admit that something unusual is happening. The persistence of shadows around 3I Atlas, combined with its unique chemistry and plume, suggests that the natural explanations themselves may not be straightforward. It may not be just fragments or just dust clumps, but a complex interplay of both. Imagine a nucleus breaking apart while also venting large carbon-rich grains, which then cluster electrostatically near the remaining core. Add in unusual gas dynamics from CO2 jets, and the result could easily resemble a swarm of satellites. The real test will come as 3I Atlas approaches and then passes perihelion. If the companions disperse with time, scattering into a diffuse tail, the natural explanations will be strengthened. If they persist, maintaining formation, the mystery will deepen. Astronomers are watching closely, not only because of the alien speculation, but because the physics of such a process could expand our understanding of cometary science. Each interstellar visitor is a case study in the diversity of planetary systems, and 3 Atlas may be showing us a form of activity that our solar system rarely produces. Fragments and dust clouds also carry broader implications. If interstellar comets regularly break apart, they may litter their paths with debris across the galaxy. Each fragment could be a sample of alien chemistry, a tiny shard of another star system's history. If dust clouds cling together in unusual ways, they could help explain how planetary systems seed the interstellar medium with complex materials. Far from being mundane, these natural processes tie directly into the big questions of how planets form, how systems evolve, and perhaps even how life's ingredients spread across space. From a human perspective, the mundane explanation is also the most profound. If the swarm is dust, it means we are witnessing alien dust, material forged around another sun, carried across light years, now visible through our telescopes. If the swarm is fragments, then those pieces are alien rocks, ripped from a nucleus that was once part of a star system we will never see. In both cases, the mystery is no less awe-inspiring for being natural. The cosmos has delivered us relics from another world, and their behavior is teaching us how little we know about the diversity of planetary debris. So could the swarm be fragments or dust clouds? Absolutely. In fact, it is the most likely explanation. But likely does not mean dull. These fragments are not simply debris. They are chapters of a story billions of years long, carried through interstellar darkness and revealed only briefly in our skies. Whether or not technology is involved, the natural drama of ice, dust, and sunlight is more than enough to capture our wonder. For in the end, even shadows drifting around a comet are messengers of cosmic history, reminding us that the universe is alive with mysteries, both natural and extraordinary. Predicted behavior as it approaches perihelion. Every comet tells a story as it nears perihelion, the point in its orbit where it comes closest to the Sun. For 3I Atlas, this moment holds extraordinary weight. Unlike ordinary comets, which return every few years or centuries, this interstellar visitor is a one-time guest. Once it swings past the Sun, it will disappear forever into the darkness of interstellar space. That means its perihelion passage is our only chance to watch how it behaves under extreme solar heating, and predictions about what might unfold are as fascinating as they are uncertain. The first expectation is an increase in brightness. As 3 Atlas draws nearer, solar radiation will heat its surface, driving more vigorous sublimation of ices. This process should expand its coma, intensify its tails, and potentially release more fragments into space. Already unusual for its CO2-dominated chemistry, 3I Atlas may flare dramatically as hidden layers of volatile ices erupt. For astronomers, such a brightening would be both an opportunity and a challenge. The comet might become easier to see, but its activity could overwhelm attempts to isolate the nucleus, making measurements of size and structure even harder. The second major prediction involves fragmentation. Many comets fail to survive their close approach to the Sun. Structural weakness, thermal stress, and violent outgassing often combine to shatter them. Historical examples abound. Comet Ison, hailed as the comet of the century in 2013, disintegrated at perihelion, leaving only a faint smear of dust. Comet Atlas in 2020, ironically sharing part of its name with our interstellar visitor, also broke apart before reaching its closest approach. If fragile, 3I Atlas could share their fate, splintering into dozens of pieces. If that happens, the swarm of dark companions might multiply rapidly, filling the sky around it with debris. What looks like mystery now could soon become chaos. Yet there are reasons to believe 3I Atlas might endure. Its suspected mass, possibly greater than expected for a comet of its brightness, suggests it could be denser and sturdier than typical solar system comets. If its nucleus is more rock-like than porous, it may resist breakup, maintaining cohesion even under solar stress. Such resilience would defy expectations but would also fit its pattern of oddities, a visitor that refuses to behave like anything we know. In this scenario, the swarm might thin rather than grow, with fragments dispersing as the main body sails on intact. The behavior of its dust is another critical factor. Polarimetric studies already show that 3I Atlas produces unusually dark, large grains. As perihelion approaches, these grains will be released in greater numbers. Unlike fine dust, which solar radiation quickly sweeps into long tails, larger clumps resist dispersal. They may linger around the nucleus, sustaining the illusion of companions. If the comet brightens while still maintaining this cloak of shadowy grains, the swarm narrative will only intensify. To casual observers, it may appear as though the nucleus is surrounded by satellites holding formation. The mysterious sunward plume also complicates predictions. If the plume continues or strengthens near perihelion, it may create dramatic structures in the coma. Some models suggest that vents angled inward could expel jets of CO2 directly toward the Sun, temporarily overpowering radiation pressure. If true, perihelion could produce spectacular, counterintuitive visuals. Tails and plumes pointing both away from and toward the Sun at once. For scientists, this would provide rare data on jet dynamics. For the public, it would deepen the sense of uncanny behavior, fuel for both fascination and speculation. Another prediction concerns gas composition. Thus far, carbon dioxide has dominated 3I Atlas's coma, with water vapor surprisingly weak. But as the comet heats further, deeper layers of ice may begin to sublimate. If water finally emerges in significant amounts, the CO2 to H2O ratio could shift, bringing it closer to solar system norms. On the other hand, if carbon dioxide remains dominant even under intense heating, it would confirm that the comet's chemistry is genuinely alien. Watching the balance change or not change will tell astronomers much about its origins and structure. Astronomers also expect volatile activity cycles. As sunlight penetrates deeper into the nucleus, pockets of trapped gas could erupt violently, producing sudden outbursts. These could temporarily boost brightness by orders of magnitude, then fade as quickly as they came. Such events might generate shock waves in the coma, scatter fragments outward, or even alter the comet's spin. If multiple outbursts occur, they could create the appearance of rhythmic activity, almost like pulses. From a distance, such pulses might even be misinterpreted as artificial signaling, further blurring the line between natural and speculative interpretations. A particularly intriguing possibility is rotation-driven fragmentation. Comets often spin irregularly, and outgassing jets can alter their rotation. If 3I Atlas spins up too quickly, centrifugal force could tear it apart. In this scenario, perihelion could mark the beginning of a cascade. One piece breaks off, changing the spin, leading to more breakage until the nucleus is shredded. The resulting debris field would spread along its orbit, creating not a single comet but a chain of alien fragments. Some astronomers quietly hope for this outcome, as each fragment would represent another sample of interstellar material, enriching the opportunity for study. From Earth's perspective, predictions also touch on visibility. If 3I Atlas brightens dramatically, it could become visible to the naked eye, drawing public attention much like Hale-Bopp in 1997 or Neowise in 2020. A visible interstellar comet would be a cultural event, inspiring awe, superstition, and endless speculation. If it fragments spectacularly, it might even create meteor-like showers of dust, observable through telescopes, though scientists stress that Earth is not in its direct path. Still, the imagery alone, an alien comet breaking apart in sunlight, would capture imaginations worldwide. What about the swarm? The most conservative prediction is that the companions will disperse. Radiation, gravity, and thermal forces will spread the fragments, erasing the illusion of formation. If that happens, astronomers will be able to say with more confidence that the swarm was natural. But if the companions remain close, perihelion will deepen the mystery. Stability in the face of solar stress would be difficult to explain by ordinary physics. That persistence would keep alive the idea of technology, structures, or hidden mechanisms at work. There is also the question of survival after perihelion. If 3I Atlas endures intact, it will gradually fade as it recedes, offering astronomers months of post-perihelion observation. If it disintegrates, it may vanish quickly, leaving only faint debris trails. Each outcome carries scientific rewards. A surviving comet allows study of long-term interstellar activity. A disintegrating one offers a direct look at alien fragments and dust. Either way, perihelion is the pivot point, the climax of its brief visit. Speculation, of course, extends further. Some enthusiasts imagine that perihelion could trigger something deliberate, an activation event. In this narrative, the swarm might rearrange, the plume might intensify, or signals might emerge. While most scientists reject this idea, it reflects the deep fascination such objects inspire. The notion that perihelion could reveal intention rather than chaos underscores how close the line is between science and story when dealing with the unknown. What is certain is that perihelion will test every theory. If the comet behaves like others, brightening, fragmenting, and then fading, it will reaffirm natural explanations. If it behaves differently, maintaining companions, preserving a plume against the sun, or refusing to shed water, it will strengthen the case that interstellar comets follow their own rules. Whatever happens, astronomers will be watching with every tool available: Hubble, Webb, ground-based telescopes, even amateur setups. This convergence of attention ensures that no detail will go unrecorded. Ultimately, the predictions reflect more than curiosity about one object. They represent humanity's attempt to anticipate how alien matter responds to familiar forces. Every comet that nears the sun tells us something about chemistry, physics, and fragility. But with 3I Atlas, the stakes are higher. Its behavior at perihelion may reveal just its own secrets, but patterns shared by countless interstellar wanderers. In its flare or its fracture, in its swarm or its silence, we may glimpse the larger truth, that the galaxy is full of travelers like this, each carrying a fragment of a distant world story. And when the day comes, as 3I Atlas skims close to the sun, we will watch not just with telescopes, but with imagination. Will it blaze brighter than expected, scatter into pieces, or hold together against the odds? Will its companions disperse into dust, or will they linger like shadows clinging to their master? These are the questions that hang in the balance as it approaches perihelion. The answers, when they arrive, will mark the climax of one of the most extraordinary astronomical events of our time, a once-in-eternity performance by a visitor from another star. Observational opportunities and challenges. Every interstellar object that drifts into our solar system presents both a golden opportunity and a daunting challenge. With 3I Atlas, those stakes are even higher. Its strange chemistry, unusual dust, and the controversial swarm of dark objects have made it one of the most discussed astronomical events in recent history. Yet observing such a fleeting alien traveler is anything but straightforward. The opportunities are profound. Insights into another star system, tests of comet physics under extreme conditions, and perhaps even clues about the spread of life across the galaxy. The challenges, however, are equally formidable. Technical limitations, timing constraints, and the distortions of distance and perspective. To understand 3 Atlas fully, astronomers must walk a razor's edge between what is possible and what is beyond our reach. The first great opportunity lies in spectroscopy. Instruments like those aboard the James Webb Space Telescope, JWST, and ground-based observatories such as the Very Large Telescope, VLT, can dissect the light from 3I Atlas, revealing its molecular composition. Already, spectroscopy has uncovered the surprising dominance of carbon dioxide in its coma, a stark contrast to water-rich comets from our own system. As the comet approaches perihelion, spectrographs can track changes in composition, telling us whether water eventually emerges in greater quantities or whether CO2 continues to rule. This is a once-in-a-lifetime chance to study how interstellar ices behave under solar heating. But spectroscopy has limits. Faint signals, interference from the coma, and the sheer brightness of the sun near perihelion can all complicate results. Polarimetry offers another invaluable opportunity. By measuring the polarization of scattered light, astronomers can deduce the size, shape, and texture of dust grains. For 3 Atlas, polarimetry has already revealed unusually dark, possibly carbon-rich grains that scatter light in alien ways. Continued polarimetric monitoring could show how these grains evolve under solar stress, whether they fragment, cluster, or change composition. Yet here too, the challenges are immense. Polarimetry requires exquisite precision, and signals can be easily contaminated by background stars or atmospheric effects. For a fast-moving faint object like 3 Atlas, every measurement demands careful calibration. Direct imaging represents both the dream and the frustration. Hubble and JWST can capture high-resolution images of the comet and its surrounding swarm. Amateur astronomers with modest telescopes can also contribute, adding to the global dataset. Together, these images may clarify whether the companions around the nucleus are real fragments, clumps of dust, or mere illusions. But no telescope on Earth or in space today has the resolution to photograph the nucleus directly. At best, we can infer its size and shape from brightness and activity. The most tantalizing details, surface features, cracks, and jets, remain forever hidden unless a spacecraft could be dispatched to intercept it. Given the timing and velocity of interstellar visitors, such a mission is nearly impossible with current technology. Timing is another critical challenge. 3I Atlas is a transient visitor, visible for only months before fading into the black. Every observation must be planned quickly, coordinated across multiple observatories, and repeated often enough to track changes. This requires global collaboration on an unprecedented scale. Astronomers in both hemispheres must hand off observations as the comet moves across the sky. Satellites like Hubble and Webb must schedule precious time for it, competing with thousands of other targets. The sheer logistics of watching 3I Atlas push human observational infrastructure to its limits. Brightness presents a paradox. As 3I Atlas nears the sun, it should brighten, making it easier to detect and analyze. But proximity to the sun also means glare, scattering, and limited observing windows. Ground-based telescopes cannot safely point too close to the sun. Even space telescopes like Hubble have restrictions. Some of the most critical moments, perihelion, fragmentation, or dramatic outbursts, may occur when the comet is nearly lost in solar brightness. Instruments designed to watch the sun, like SOHO or Parker Solar Probe, may become essential, but they are optimized for solar physics, not faint interstellar visitors. the most exciting activity could unfold just out of reach of our clearest eyes. Amateur contributions form an underrated opportunity. Across the world, skilled amateur astronomers with sensitive cameras can monitor 3I Atlas nightly, tracking brightness variations and coma shape. Collectively, these observations provide continuous coverage that professional telescopes cannot match. Citizen science networks, already vital in asteroid and comet tracking, have rallied around 3I Atlas. Yet amateur data also carry risks: uneven quality, misinterpretations, and artifacts that feed speculative narratives. Balancing grassroots enthusiasm with professional rigor is essential to prevent confusion about what is real and what is illusion. Radar, a powerful tool for near-Earth asteroids, is unfortunately ineffective here. 3I Atlas is simply too far and too faint to bounce radar signals back to Earth. That eliminates one of the best methods for measuring size and shape directly. Instead, astronomers must rely on indirect methods: brightness curves, thermal modeling, and coma subtraction. These all introduce uncertainties that fuel debates over whether the nucleus is a few hundred meters or several kilometers across. The lack of radar data is a reminder that interstellar visitors expose the limits of our toolkit. One of the greatest opportunities of all lies in cultural impact. Few astronomical events grip the public imagination like interstellar visitors. Every image of 3I Atlas carries not just scientific weight, but symbolic power. For many, it represents contact with the wider galaxy, even if only through ice and dust. The swarm of shadows, whether fragments or artifacts, has already sparked global speculation. This cultural momentum drives attention, funding, and curiosity in ways no ordinary comet could. But managing that attention is a challenge. Scientists must communicate carefully, avoiding both hype and dismissal. Too much hype risks disillusionment. Too much dismissal risks alienating the public. Coordinating multi-wavelength observations is another unique opportunity. Ground-based optical telescopes capture brightness and coma evolution. Infrared instruments like JWST probe the chemistry of ices. Radio telescopes can detect faint emissions from specific molecules. X-ray observatories may even detect solar-wind interactions. Together, this multi-wavelength approach can build a complete picture of 3I Atlas, from its nucleus to its tail. But coordination across facilities, nations, and budgets is no simple task. It requires global collaboration at a scale usually reserved for missions like gravitational wave detection or exoplanet surveys. 3I Atlas, in its brief passage, forces scientists to unite. The unpredictability of comets itself adds both opportunity and challenge. Outbursts, fragmentations, and sudden brightness changes can occur at any moment. These events, if caught, provide invaluable data. If missed, they become mysteries, known only through rumors or low-quality images. For 3I Atlas, every unexpected behavior matters more, because each anomaly could reflect the alien conditions of its origin. Yet telescopes cannot watch continuously. Inevitably, some events will escape notice, leaving gaps in the record. The biggest challenge of all is finality. Once 3I Atlas passes through, it will never return. Its hyperbolic trajectory ensures it will leave the solar system forever, fading into the galaxy. That makes every missed opportunity permanent. With periodic comets, astronomers can wait for another orbit, another chance. With 3I Atlas, there are no second chances. This knowledge weighs heavily on the scientific community. Each lost observation feels like a door closing on the universe's secrets. Still, the opportunities outweigh the frustrations. Already, 3I Atlas has broadened our understanding of comet chemistry, dust behavior, and interstellar diversity. It has revealed that not all comets are water-dominated, that alien dust can be darker and denser, and that activity can defy expectations. As perihelion nears, every instrument trained on it may uncover more surprises. Whether it fragments or endures, whether its swarm disperses or persists, it will leave behind a record that will shape astronomy for decades. For humanity, the challenge is to accept both the limits of our tools and the magnitude of the moment. We cannot know everything about 3 Atlas, but what we can know is precious, a glimpse of chemistry from another world, a test of our observational ingenuity, and a reminder that the galaxy is full of wanderers crossing unseen between stars. Observing them will never be easy, but each time we succeed, even partially, we expand the horizon of human knowledge. 3I Atlas is, in a sense, a mirror. Its opportunities and challenges reflect our own strengths and weaknesses, our technology, our collaboration, our imagination. It reminds us that astronomy is not just about the objects we study, but about our ability to rise to the occasion when the cosmos sends us a messenger. And whether we see dust, fragments, or something stranger, we will carry the lessons of this fleeting visitor long after it has vanished into the night. What this could mean for comet science and interstellar science. When astronomers first confirmed that 3I Atlas was interstellar, the significance was clear. This was only the third such visitor humanity had ever observed. Oumuamua and Borisov had already expanded our understanding of what was possible, but 3I Atlas arrived with its own peculiarities, its swarm of companions, its strange sunward plume, its unusual CO2-dominated chemistry, and its unusually dark dust grains. Each of these traits is interesting on its own. Taken together, they suggest that our ideas about comets, both local and interstellar, may be incomplete. The lessons from 3I Atlas ripple outward, forcing us to rethink not just how comets behave, but how planetary systems form, how material travels between stars, and how interconnected the galaxy may be. For comet science, the most immediate implication is diversity. For centuries, comets within our solar system have been studied, categorized, and modeled. They are volatile, rich objects from the Oort cloud or Kuiper belt, usually dominated by water ice with carbon monoxide and carbon dioxide as secondary contributors. Dust tails, ion tails, periodic outbursts, these patterns became the standard. But 3I Atlas breaks that mold. Its CO2 to H2O ratio is unlike anything in our system. Its jets behave unpredictably. Its dust is darker and denser. These differences reveal that comets are not universal. They are products of their home systems, reflecting unique chemistry and environments. This realization reshapes assumptions about planet formation. Comets are the leftover building blocks of planetary systems, frozen relics from the disks of dust and gas that surround newborn stars. By studying them, astronomers infer conditions in those disks billions of years ago. If 3I Atlas formed in a region where carbon dioxide dominated over water, then its parent star's disk must have had different temperature gradients, radiation levels, or chemical abundances than ours. Multiply that by billions of stars in the galaxy, and a picture emerges. Every planetary system leaves behind a distinct fingerprint in its comets. That means every interstellar comet we encounter is a sample return mission from another world's history. The swarm debate also carries meaning for comet science. If the companions are fragments, it suggests that interstellar comets may be particularly prone to fragmentation. Perhaps the stresses of long interstellar travel, cosmic radiation, thermal cycling, micrometeorite impacts make them more brittle than local ones. Alternatively, if the swarm is dust clumps bound by electrostatic forces, it may reveal that interstellar dust behaves differently, clustering instead of dispersing. Either outcome forces revisions to models of comet disintegration and dust dynamics. For scientists who build simulations of how comets evolve, 3I Atlas is already a disruptive data point. For interstellar science, the implications are even more profound. Until 2017, interstellar objects were hypothetical. Astronomers assumed they existed. After all, planetary formation naturally ejects debris, but none had ever been seen. Now, within less than a decade, 3 have been observed. That suggests the galaxy is teeming with them, crossing through planetary systems all the time. 3I Atlas is not an outlier, but part of a vast, hidden population. For interstellar science, this transforms how we view galactic exchange. Planetary systems are not closed boxes, they are porous, constantly trading material. Rocks, ices, and dust from one star's nursery wander into the realms of others. The galaxy is a dynamic marketplace of debris. This has direct implications for panspermia, the idea that life's building blocks, or even life itself, can spread between stars. 3I Atlas carries carbon-rich molecules, possibly including formaldehyde and complex hydrocarbons. These are precisely the compounds thought to seed early life. If such objects are common, then the transfer of prebiotic material may be widespread. It does not prove panspermia, but it makes it more plausible. Interstellar comets, like 3I Atlas, may have delivered organics to Earth in the deep past or to other worlds across the galaxy. The line between isolated planetary systems and a connected galactic ecosystem becomes blurrier. The unusual chemistry of 3I Atlas also sharpens the search for habitable worlds. If comets are so diverse, then the planets they helped form must be equally varied. Some may have been seeded with CO2-rich comets, creating atmospheres with very different greenhouse balances. Others may have received nitrogen-rich comets, shaping climates in unexpected ways. Studying 3I Atlas is not just about one comet, it is about expanding our catalog of possible planetary recipes. The more we understand, the better we can interpret exoplanet atmospheres and biosignatures. When telescopes detect unusual gases around distant worlds, comets like 3I Atlas remind us that alien chemistry is the norm, not the exception. Another implication lies in survivability. 3I Atlas may have been wandering the galaxy for millions or billions of years. That it remains intact suggests resilience. Either it was ejected with extraordinary strength, or interstellar comets are more durable than we expected. If so, then trillions may survive across the galaxy, acting as messengers from ancient systems. This durability ties back to panspermia. If ices and organics can survive for eons, then they can cross not just interplanetary but interstellar distances. That expands the horizon of where and how life might arise. For technology and observation, 3I Atlas is also transformative. Every new interstellar object pushes astronomers to improve detection methods. Wide-field surveys like ATLAS, Pan-STARRS, and the upcoming Vera-Rubin Observatory are being fine-tuned to spot such visitors earlier and track them longer. The discovery of 3I Atlas is already shaping priorities for future telescopes. In the long run, this may lead to missions designed specifically to intercept or rendezvous with interstellar objects, a feat that seemed like science fiction only a decade ago. Each discovery fuels momentum toward turning speculation into strategy. The controversies surrounding 3I Atlas also reveal something important about science itself. Alien probe theories, though speculative, highlight the limits of our models. When natural explanations fail to fit neatly, imaginations rush to fill the gap. This is not just public fantasy, but a reminder that our frameworks are incomplete. Even if the swarm is dust, the fact that it looks so much like structure challenges our understanding. For comet science, that is progress. Anomalies drive refinement. For interstellar science, it is a warning. Expect the unexpected. The diversity of the galaxy is greater than our categories. At a cultural level, the comet reinforces humanity's cosmic perspective. Seeing an object from another star system is like shaking hands with the galaxy itself. For comet science, it validates decades of study by showing that our models have relevance beyond our solar system. For interstellar science, it proves that we are not isolated. Material flows between worlds. In that sense, 3I Atlas is not just a comet. It is a messenger, reminding us that Earth is part of a larger galactic story. Looking forward, what 3I Atlas means for comet and interstellar science is transformation. It forces scientists to expand their assumptions, to incorporate alien chemistry, to consider new dust behaviors, and to refine models of fragmentation and survivability. It proves that interstellar debris is not rare but constant. It strengthens the case that organic chemistry is widespread, perhaps universal. It encourages the search for future interstellar visitors with better telescopes and faster missions. It ignites debates that stretch beyond science into culture, myth, and philosophy. In the end, the meaning of 3 Atlas lies in its dual nature, both ordinary and extraordinary. Ordinary because it is just another piece of debris, one of trillions. Extraordinary because it carries the fingerprints of another sun, crossing light years to tell us a story. For comet science, it expands the definition of what a comet can be. For interstellar science, it confirms that the galaxy is interconnected. And for humanity, it offers a glimpse into the deep processes that link star systems into a single shared cosmos. As it fades into the dark after its brief visit, 3I Atlas will leave behind more than data. It will leave questions, models, and possibilities that reshape two fields at once. Comet science will never again be confined to our solar system. Interstellar science will never again be abstract. The two have merged, bound together by a dusty, shadowed traveler that came from beyond and reminded us that the universe is stranger, richer, and more connected than we had ever dared to imagine. Conclusion and open questions. When 3I Atlas first appeared in our skies, it seemed destined to be just another interstellar curiosity, a follow-up to Oumuamua and Borisov. Yet in the months since its discovery, it has proven to be far more than that. Its strange swarm of dark companions, its unusual CO2-driven chemistry, its sunward plume, and its stubborn refusal to conform to the rules of solar system comets have forced astronomers to rethink what they thought they knew. And as it speeds toward perihelion, the climax of its brief encounter with our sun, the comet leaves us with as many questions as answers. In one sense, the conclusion is simple. 3I Atlas is a messenger from beyond, carrying with it the fingerprint of another star system. It proves once again that the galaxy is not static, but alive with travelers, with material crossing between systems in a slow but constant exchange. It confirms that our models of comets must account for chemistry and physics beyond the boundaries of our solar system. It demonstrates that interstellar comets are not rare oddities but likely abundant, and that each one we detect is a unique sample of alien history. On this level, the comet is a triumph for astronomy, a validation of decades of theory, and a harbinger of discoveries yet to come. But beneath that straightforward conclusion lies a field of open questions, unresolved mysteries that will echo long after 3 Atlas has vanished into the night. The swarm remains the most tantalizing of these puzzles. Are the companions real, stable fragments? Are they merely clumps of dust masquerading as structure? Or are they something stranger still, devices, probes, or engineered escorts? Even cautious astronomers acknowledge that their behavior is unusual. Until observations clarify whether the swarm disperses or persists after perihelion, the debate will continue. If it disperses, natural explanations will be strengthened. If it persists, the door to speculation will stay open. The sunward plume raises another enduring question. Comet tails are supposed to point away from the sun, driven by solar wind and radiation pressure. Why does 3I Atlas vent material toward the sun instead? Are we witnessing jets shaped by topography, angled in just the right way? Or is there a deeper, poorly understood mechanism at play, perhaps unique to interstellar chemistry? For now, the plume defies easy explanation, leaving a gap in comet science that future models will need to fill. Composition is another open frontier. JWST's early observations revealed the dominance of carbon dioxide, but mysteries remain about deeper layers. Will water emerge as perihelion approaches, or will CO2 continue to define its character? Does its chemistry represent a unique system, or a whole class of comets from colder, more distant planetary nurseries? The answers matter not just for 3I Atlas, but for exoplanet science as a whole. Each new data point reshapes our understanding of how planetary systems evolve and what they leave behind. The question of survivability also hangs in the balance. Will 3 Atlas shatter under solar stress, scattering fragments across the void? Or will it endure intact, a stubborn, resilient traveler? Its fate will teach us much about the strength of interstellar material. If it breaks, we learn about brittleness. If it survives, we learn about durability. Either way, its resilience, or fragility, will inform models of how comets fare during million-year journeys through interstellar space. And then there is the deeper, more speculative question. What role do interstellar comets play in the grand story of life? If 3 Atlas carries organics, as evidence suggests, could such visitors be agents of panspermia, scattering the seeds of biology across the galaxy? Did Earth itself once receive such gifts from beyond? Could 3I Atlas be carrying not just carbon and dust, but the raw potential of life, frozen and preserved across unimaginable time? These questions may never be answered directly, but they frame the way humanity sees itself. Not as an isolated species on an isolated planet, but as part of a galactic network where even frozen rocks participate in the story of life. The challenges of observation leave their own open questions. How much have we missed? How many fragments or outbursts have gone unrecorded while the comet sat in the glare of the sun? How many details will be lost forever once it recedes into darkness? Each interstellar visitor is a reminder of our limitations, of the gap between what we want to know and what our instruments can capture. Until we send spacecraft to intercept such objects, much will remain out of reach. Even the philosophical dimension lingers as an open question. Why do objects like 3I Atlas so easily ignite speculation about alien technology? Is it simply human imagination at work, or is it a deeper instinct, a yearning to see meaning in the unknown? The debate over probes, motherships, and swarms says as much about us as it does about the comet. It reveals our hunger for contact, our fear of solitude, and our willingness to project our stories onto the cosmos. Whether the swarm is dust or design, the way we talk about it reveals humanity's place in the universe, always searching, always wondering. In the end, the conclusion is less an answer than a balance. 3 Atlas is both natural and mysterious, both ordinary and extraordinary. It is almost certainly a comet, a frozen relic from a distant sun, carrying chemistry that reflects its alien nursery. And yet, its anomalies are real, and they demand attention. Its swarm, its plume, its composition, its resilience. Each of these invites questions that remain unresolved. The comet leaves us humbled, reminding us that even with our telescopes, satellites, and theories, the universe retains its secrets. What does 3I Atlas mean for science? It means cometary models must expand. It means interstellar science has moved from theory to observation. It means planetary systems are not closed but porous, exchanging matter across light years. It means the galaxy itself may be threaded by streams of wandering debris, each carrying chemistry and stories from another world. It means panspermia, once dismissed as speculation, deserves serious consideration. And it means humanity must prepare. This will not be the last interstellar visitor. With instruments like the Vera Rubin Observatory coming online, many more will be detected in the coming decades. Each one will bring its own surprises, its own open questions, its own chance to reshape our understanding. And so we are left with a paradox. We know more than ever before about interstellar comets, and yet we are more aware than ever of how little we know. 3 Atlas, like its predecessors, has expanded our horizons not by providing final answers, but by multiplying mysteries. It reminds us that the cosmos is not static, but dynamic, filled with travelers and secrets. It tells us that science is not just about solutions, but about wonder, about the pursuit of questions that may never be fully resolved. As 3I Atlas fades into the outer reaches of the solar system and then into the galactic night, its legacy will endure. It will remain a marker in the history of astronomy, a visitor that arrived, puzzled, and departed, leaving scientists with data, debates, and dreams. Its swarm will remain a symbol, whether of dust clumps or of possibilities, of how the unknown always hovers at the edge of knowledge. Its plume will remain a puzzle, its chemistry will remain a case study, and its presence will remain a reminder that we are part of a galaxy alive with movement. The open questions may outlast the answers. That is not failure, but success. Science advances not only when mysteries are solved, but when new mysteries are revealed. 3I Atlas has done that in abundance. Its story is unfinished, and perhaps it always will be. But in that unfinished story lies the greatest gift, a sense of wonder that stretches beyond the sun, beyond Earth, and into the infinite night. In the end, 3I Atlas has reminded us of something essential, that the universe is bigger, stranger, and more interconnected than we can yet imagine. Its conclusion is not an ending, but an invitation to keep looking, to keep questioning, to keep our eyes and our minds open to the mysteries that travel between the stars. And its open questions, unanswered as they are, may prove to be the most enduring legacy of all.